In this journey through the James Webb Space Telescope's latest revelations, we will explore the impossible scale of a cosmos that is far larger and older than we ever dared to imagine. As you settle into this quiet space of learning, let your mind drift across the vast distances of the infrared universe, where time and light become one. The universe we thought we knew was a place of measurable boundaries, a sphere stretching 14 billion light-years in every direction. But the James Webb Telescope has just revealed that our perspective is just part of the truth. We are now standing at the edge of a reality that spans 93 billion light-years across, a distance so immense that the human mind cannot truly grasp it, yet we can feel its weight in the silence of the stars. This telescope, a marvel of gold and glass, looked into a patch of sky that appeared to be nothing more than empty velvet darkness. It stared for hours, patiently waiting for the oldest photons in existence to arrive at its mirrors. What it found was nearly 800,000 galaxies hiding in that single pocket of shadow. These are not just distant lights, they are ancestral structures that formed when the cosmos was only 300 million years old. They are ghosts of a time when the universe was in its infancy, yet they possess a complexity that defies every law of physics we have written. We have found black holes billions of times more massive than they should be, and structures stretching tens of millions of light-years across at a time when there simply was not enough time for them to grow. Everything we believed about the universe's size and pace was wrong. To understand how this mirror looks through time, we must first understand the nature of light itself. Light takes time to travel, and because the universe is so vast, every image we see is an image of the past. When you look at something only a mile away, you see it as it was 5 microseconds ago. It is a tiny, negligible delay, but it is there. When you look at the moon hanging silver in the night sky, you are witnessing it as it was 1.3 seconds in the past. If the moon were to vanish in an instant, you would continue to see its glow for a heartbeat longer than its existence. When you gaze at the nearest star, you are witnessing light that began its journey 4 years before today. This is the fundamental truth of astronomy. Every photon crossing the freezing void of space carries an image of its beginning. Every star you see is a message from a different era. The deeper we look into space, the further we look back into the history of everything. The James Webb Space Telescope sits 1 million miles from Earth, far away from the heat and interference of our world, staring eternally into the darkness. Its mirror stretches 21 feet across, a honeycomb of beryllium coated in a thin layer of gold. This gold is not for decoration. It is specifically designed to catch infrared light. Infrared light is the secret language of the deep universe. Think of it as what remains after visible light has been stretched by the relentless expansion of the universe. To visualize this, imagine a siren passing you on a long, straight highway. As the vehicle approaches, the sound is high and sharp. As it passes and moves away, the sound drops lower and lower, the waves stretching out behind it. Light does the same thing across cosmic distances. As galaxies move away from us at incredible speeds, the light they emit is stretched. The tight, blue waves of ultraviolet light become the long, slow waves of red and eventually infrared. This is why the James Webb Telescope is vital. The most distant galaxies are moving away from us so fast that their light has shifted entirely out of the range of human vision. They are invisible to our eyes and even to telescopes like Hubble. But to Webb, they blaze with a ghostly ancient heat. It is not just looking far away, it is looking backward through time itself, peeling back the layers of cosmic history until it reaches the very first moments of light. The most distant galaxy found by this golden eye emitted its light 13.5 billion years ago. To hold that number in your mind is to realize that we are seeing this galaxy as it appeared when the universe was only 290 million years old. If we were to compress the entire age of the universe into a single calendar year, this galaxy formed on the 2nd day of January. The light traveling toward us has been moving through the void for almost the entire history of existence. When that light began its journey, the Earth did not exist. Our sun had not yet ignited. The Milky Way was nothing but a chaotic collection of cosmic gas, slowly pulling itself together. While these photons crossed the emptiness, the stars formed, the planets cooled, dinosaurs walked the earth, and human civilization rose and fell. All of history occurred while these tiny particles of light were mid-flight. Every image Webb captures is a fossil. It is a preserved moment frozen in light, a snapshot of a universe that no longer exists in that form. The patience required to see this is staggering. The telescope must gather these ancient photons for 10 hours or more just to capture a single galaxy. 10 hours of silent waiting for light that has been traveling for 13.5 billion years. Scientists confirm these impossible distances using an instrument called a spectrograph. This device works like a prism, splitting the arriving light into its component colors, creating a rainbow of data. Within that rainbow, there are specific patterns that reveal how fast the universe has been expanding since the light was first emitted. The farther away something is, the more its light has been stretched toward the red end of the spectrum. This is called redshift. One particular galaxy showed a redshift of 14.32, the highest ever recorded for a confirmed galaxy. This tells us that we are not just observing distant objects, we are witnessing the childhood of the cosmos. We are seeing the first structures that would eventually lead to everything we know. Every star you see tonight, every planet in our solar system, and even every atom in your own body can trace its origin back to these early frantic moments of creation. But as we look deeper, we find problems that we never anticipated. We see objects that are too bright and too large for their age. We see a galaxy with a name like a serial number, Jade's GSZ14-0. When astronomers spotted it in the late months of 2023, they spent months doubting their own data. It appeared too developed, too massive to exist in an era when the first stars were supposed to be just flickering into existence. It suggests that the universe's timeline needs to be rewritten. The Webb mirror is showing us a past that is far more crowded and active than our theories allowed. As you listen to the rhythmic expansion of these thoughts, let yourself feel the scale of this discovery. We are finally seeing the true face of the beginning. We are watching the dawn of time itself, reflected in a golden mirror 1 million miles away. Every image captured by the James Webb Space Telescope is essentially a fossil, a preserved moment in time that has been frozen in the medium of light and carried across the vacuum for eons. To look at the deep field images provided by this golden observer is to walk through a museum of the entire history of the cosmos. As we move deeper into the story of these ANC records, it is important to understand that the light we are catching today is not a live broadcast, but a message from a world that has long since changed or disappeared. The photons that strike the telescope's sensors today have been traveling through the expanding darkness for billions of years, surviving the birth and death of countless stars, the collision of galaxies, and the very stretching of space-time itself. This light is a biological and chemical record of the universe's earliest breaths. When we analyze these fossilized rays, we find that they carry the signatures of the very first elements created after the Big Bang. To appreciate the scale of these fossil records, consider the sheer emptiness that these light particles had to traverse. Between us and the most distant galaxies lies a void so immense that it defies human language. Yet, these tiny packets of energy, these photons, have maintained their integrity. They have traveled in a straight line, mostly undisturbed, through a universe that was constantly growing larger around them. This brings us to the realization that the James Webb Telescope is not just a camera, but a time machine of unprecedented power. By the time the light from a galaxy 13 billion light-years away reaches the 21-foot golden mirror, it has been stretched and weakened, but it still contains the structural details of that galaxy's infancy. We are seeing the universe as it was when it was less than 5% of its current age. For perspective, if the universe were a human being who lived to be 80 years old, Webb is showing us pictures of that person when they were only a toddler, barely learning to walk and speak. What makes these fossil records so fascinating is the detail they reveal about the composition of the early universe. Scientists use an instrument called a spectrograph to read the DNA of this ancient light. By splitting the light into a spectrum, they can see dark lines representing different chemical elements. These lines are like a barcode that tells us exactly what that distant galaxy was made of billions of years ago. In the nearby universe, we see a rich variety of elements: carbon, oxygen, nitrogen, and iron, all of which are produced in the hearts of stars and scattered when those stars explode. But as we look at the older fossils, the older light, we see a universe that was much simpler. We find galaxies that are composed almost entirely of hydrogen and helium, the original ingredients of the Big Bang. These are the pristine records of a time before the universe was polluted by the heavier elements that make up our bodies and our planet. The most remarkable fossilized galaxy Webb has studied is known as Jade's GSZ 14-0. This object is so distant that its light began its journey only 290 million years after the beginning of time. When we look at this record, we are seeing something that theoretically should not be as bright or as large as it appears. It contains several 100 million times the mass of our star, all packed into a relatively small area. The light comes from young blazing stars that were producing massive amounts of ultraviolet radiation. However, because the light has been traveling for so long through expanding space, those ultraviolet waves have been stretched by a factor of 15. What was once blue and energetic light is now arriving as long, slow infrared waves. Webb's ability to detect this specific shift is what allows us to date these fossils with incredible precision. This process is known as measuring the redshift. For this particular galaxy, the value was the highest ever confirmed, marking it as one of the oldest fossils in the cosmic record. The discovery of such a well-developed galaxy in the very early universe is like finding a modern city in an archaeological dig where you expected to find only primitive stone tools. It suggests that the cosmic dawn, the period when the first stars began to shine, happened much earlier and much more vigorously than our previous models predicted. Gravity must have worked more efficiently, or gas must have cooled faster than we thought possible. These fossil records are forcing us to rethink the entire timeline of cosmic evolution. We used to believe that the early universe was a dark, quiet place that slowly flickered into life. Instead, Webb is showing us a vibrant, crowded, and energetic beginning. The darkness was never truly empty. It was teeming with the seeds of everything that exists today. As we continue to analyze these light fossils, we also discover the role of dark matter in shaping the early universe. While dark matter itself does not emit light and cannot be seen, its gravitational influence is etched into the distribution of the galaxies we do see. Fossil records show the galaxies were not scattered randomly. Instead, they were pulling together into clusters and filaments, following an invisible scaffolding of dark matter that had already formed. This scaffolding acted as a blueprint for the cosmic web, the largest structure in existence. The light we see today is the visible decoration on an invisible monument that was built in the first moments after the Big Bang. There is a certain peace in realizing that the light from these ancient galaxies has been traveling toward us for 13.5 billion years, just so that we could finally build the technology to catch it. These photons are the ultimate survivors. They have crossed the dark ages of the universe, a time when the cosmos was filled with a thick fog of neutral hydrogen that blocked most light. Eventually, the radiation from the first stars and galaxies cleared this fog in a process called ionization, making the universe transparent. The fossils Webb is finding are the very objects that performed this monumental task. They are the lamps that lit up the darkness and allowed the universe to be seen. When you think about these fossil records, it helps to imagine the sheer scale of the journey. During the time these photons were in flight, our own galaxy was just a chaotic swirl of gas. Our solar system didn't exist. The Earth was not even a thought in the mind of the cosmos. Entire generations of stars lived and died, creating the oxygen you breathe and the carbon in your cells, all while this ancient light was still mid-journey through the void. By looking at these images, we are connecting with a past that is so distant it feels mythological, yet it is as real as the ground beneath your feet. We are descendants of those early structures. We are the living proof of the processes that Webb is capturing in these frozen moments of light. The fossils of the early universe are not just distant curiosities, They are our own history, written in the stars and delivered to us across the ocean of time. Every pixel of a Webb image contains a story of survival, a record of the persistent and enduring nature of light in a universe of shadow. The era known as the cosmic dawn represents the most mysterious and fundamental transition in the history of everything. It was the moment the universe moved from a state of absolute cold darkness into a place of light and structure. For hundreds of millions of years following the Big Bang, the cosmos was a vast, opaque sea of neutral hydrogen gas. There were no stars to illuminate the void, and no galaxies to anchor the gravity of space. It was a period of silence and invisibility, often referred to by astronomers as the Dark Ages. But slowly, under the relentless pull of gravity, first clumps of matter began to collapse. Gas became denser and hotter until, finally, the first nuclear fires ignited. This was the beginning of the cosmic dawn, the birth of the very first generation of stars. According to every mathematical model we possessed, this process should have been slow and sparse. We expected to see small, fragile collections of stars struggling to form in the early gloom. However, the James Webb Space Telescope has pulled back the curtain on this era and found something that should not exist, an impossible galaxy that challenges our entire understanding of how the universe began. This galaxy, designated Jade's GSZ 14-0, sits at a distance that places it a mere 290 million years after the Big Bang. In the grand timeline of a 13.8 billion-year-old universe, this is a blink of an eye. At this stage, the universe was still in its infancy. Yet this galaxy is not a small or primitive cluster. It is large, it is exceptionally bright, and it is startlingly complex. When astronomers first processed the data, they were convinced it was a mistake, or perhaps a foreground object mimicking a distant light. The galaxy measures over 1,600 light-years across. While this is small compared to our modern Milky Way, it is gargantuan for its age. It contains hundreds of millions of stars, all of them burning with a fierce, young intensity. The sheer amount of light coming from this object is staggering. It is so bright that Webb could have detected it even if it were 10 times fainter. This brightness is the primary reason scientists call it impossible. To produce that much light, a galaxy needs an enormous amount of gas and a tremendous number of stars, yet there simply wasn't enough time in the standard cosmological model for gravity to have gathered that much material so quickly. Theoretical models once predict that early galaxies would be dim, simple, and incredibly rare. We figured we would have to hunt through thousands of images just to find a single faint smudge from this epoch. Instead, Jade's GSZ 14-0 was found with relative ease, and it isn't alone. Its existence suggests that the early universe was teeming with large-scale structures far earlier than we ever dreamed. This creates a fundamental crisis in physics. Gravity usually works at a predictable pace. Cold gas must lose energy to collapse, and that cooling takes millions of years. Dark matter must first create the halos or gravitational wells that trap the gas, which also takes time. But this galaxy exists as a finished product in a time frame where we expected only raw materials. It is as if we walked into a construction site only minutes after the groundbreaking ceremony and found a completed skyscraper already standing. This is why it is often referred to as a universe breaker. It doesn't just break our records, it threatens to break our current laws of cosmic evolution. As you ponder the scale of this impossible object, consider the environment in which it lived. The early universe was much smaller and much denser than it is today. Everything was packed closer together, and the temperature of space itself was higher. This should have made it harder for gas to cool and form stars, yet the opposite seems to have happened. Perhaps the efficiency of star formation was different in the primordial soup. Maybe the first stars were much more massive than the stars we see today, burning through their fuel with a brilliance that we can no longer replicate in the modern age. These stars, known as population 3 stars, were made of pure hydrogen and helium. Without heavier elements to disrupt their chemistry, they could grow to be hundreds of times more massive than our Sun. A galaxy filled with these giants, old shine with a terrifying luminosity. lighting up the cosmic dawn and ending the Dark Ages with a sudden, violent burst of radiation. This radiation is what eventually stripped the electrons from the surrounding hydrogen gas, making the universe transparent and allowing light to finally travel freely across the reaches of space. What makes JADE's GSC 14-0 even more perplexing is its chemical signature. Using the telescope's spectrograph, scientists found evidence of oxygen and other heavier elements within the galaxy. This is a profound discovery. Oxygen is not created in the Big Bang, it is forged only in the nuclear furnaces of stars. For oxygen to exist in a galaxy that is only 290 million years old, an entire previous generation of stars must have already lived, died, and exploded as supernovae to scatter those elements into the gas clouds. This pushes the timeline back further. It means that the very first stars must have ignited almost immediately after the Big Bang, perhaps as early as 100 million years into the life of the cosmos. The dawn was not a slow sunrise, it was an explosive flash that transformed the universe almost instantly. We are looking at a history that is much more compressed and energetic than we ever dared write in our textbooks. The light from this impossible galaxy has been traveling toward us for 13.5 billion years. As it moved through the expanding void, its wavelength was stretched by a factor of 15. What was once brilliant, hot, ultraviolet light has been transformed into the low, steady hum of infrared. This is the only reason we can see it today. The James Webb Telescope was built specifically to find these impossible objects by looking in the only spectrum where they still have a voice. It is a testament to human curiosity that we can sit on a small planet, orbiting a middle-aged star, and catch the light from a galaxy that existed when the universe was just a tiny fraction of its current age. We are witnessing the very first structures that would eventually lead to the formation of the Milky Way, the Sun, and our own lives. We are looking at our own ultimate ancestry. The mystery of JADE's GSC 14-0 reminds us that the universe is always more complex than our theories. Every time we build a better tool, the cosmos responds with a new surprise that forces us to be humble. We thought we knew the scale of the beginning, but the cosmic dawn has revealed a reality that is far more crowded and magnificent than we anticipated. This impossible galaxy stands as a silent sentinel at the edge of the observable horizon, a golden reminder that the darkness of the early universe was never truly empty. It was filled with the frantic, brilliant work of creation, building the foundations of everything we see tonight. As you drift deeper into the story of the stars, let the light of this distant world serve as a bridge between the beginning of time and the quiet moment you inhabit now. The discovery of massive, mature galaxies in the deep infancy of the universe has left the astronomical community in a state of profound shock, a sensation often compared to the hypothetical scenario of an archaeologist excavating a pristine, functioning smartphone from among the ancient stone ruins of the Roman Empire. When we look back at the Roman era, we expect to find clay pottery, iron swords, and marble columns, technologies that fit the chronological development of human history. To find a piece of high-tech digital circuitry buried beneath the Colosseum would not just be a surprise, it would be a fundamental violation of the timeline we understand. It would suggest that either our history is wrong or there were hidden processes at work that we never accounted for. This is exactly the crisis currently facing our understanding of the cosmos. The James Webb Space Telescope is the shovel that has dug deeper into the strata of time than any tool before it, and what it has unearthed in the earliest layers of the universe are galactic structures so sophisticated and so developed that they simply should not be there according to the established laws of physics. In the standard model of cosmology, galaxy building is a slow and arduous process. It is a cosmic construction project requiring billions of years of preparation. First, the invisible scaffolding of dark matter must settle into place, creating the gravitational wells necessary to trap primordial gas. Then, that gas must cool down significantly, a process that takes an immense amount of time because heat is difficult to radiate away in the vacuum of space. Only once the gas is cold and dense can gravity begin to fragment it into the first stars. These stars then live their lives, die and merge, slowly pulling more gas into the system to build a rotating disk or an elliptical core. We expected the first several hundred million years of the universe to be a time of prehistory, a period of small, messy and dim proto-galaxies. Instead, the James Webb Telescope has revealed objects that are bright, structured and heavy with stars, appearing just 290 million years after the Big Bang. These are the smartphones in the Roman ruins, objects that possess the technology of maturity far before their time. One of the most unsettling aspects of these early galaxies is their sheer mass. They contain hundreds of millions of stellar masses worth of material. To understand the gravity of this problem, one must realize that the universe at that age was only about 2% of its current age. It is as if a human infant were born already possessing the muscle mass and bone density of a fully grown athlete. There is a physical limit to how fast matter can be pulled together. If you try to shove gas into a central point too quickly, the resulting friction creates heat and pressure that actually pushes the gas back out, halting the growth. This is a cosmic speed limit. Yet, these universe breakers seem to have bypassed this limit entirely. They found a way to assemble themselves in a fraction of the time that our best supercomputer simulations say is possible. Scientists are now forced to ask if gravity worked differently in the high-density environment of the early cosmos, or if there is a missing piece of the puzzle, perhaps a dark force or a different type of matter, that accelerated the birth of these giants. Beyond their mass, these galaxies also show a chemical complexity that is deeply confusing. When we analyze the light from these ancient structures, we don't just see the simple signatures of hydrogen and helium. We see the fingerprints of oxygen, nitrogen, and carbon. In the analogy of the Roman ruins, this is like finding not just the smartphone, but a modern chemical laboratory. These elements are only forged in the hearts of stars through nuclear fusion, and they are only released into the wider galaxy when those stars explode as supernovae. This means that by the time we are seeing these galaxies at 300 million years old, at least one entire generation of stars has already been born, lived out its entire multi-million-year lifespan, and died in a violent explosion to seed the clouds with heavy elements. The timeline is being pushed backward with every new observation. The Roman era of the universe was apparently much more technologically advanced than we ever imagined, featuring chemical enrichment that we thought would take at least 1 billion years to achieve. This discovery has forced a massive revision of humanity's view into the cosmic past. In just its first 18 months of operation, the James Webb Telescope extended our view into the history of the universe by 40%. We are now seeing 40% deeper into the darkness than we ever thought possible with modern instruments. But with that deeper view comes a deeper mystery. If galaxies this massive and chemically rich existed this early, what else are we missing? It suggests that the dark ages of the universe, that period before light began, was much shorter than we suspected. The first stars might have ignited almost immediately after the Big Bang, turning the universe from a cold, dark void into a brilliant, star-strewn expanse in what is effectively a cosmic heartbeat. We are beginning to realize that the universe did not slowly wake up. It exploded into activity with a ferocity that defies our current mathematical models. The implications of finding these smartphones in the early strata of time reach into every corner of astrophysics. It changes how we think about the formation of black holes, which are often found at the centers of these early galaxies. If a galaxy can grow that fast, then the black hole at its center must also be growing at an impossible rate, consuming gas and stars like a gluttonous monster in a room with limited food. It changes how we think about the cosmic web, the large-scale structure that connects all matter. If the nodes of the web, the galaxies, are forming this early, then the web itself must have been spun much faster and much tighter than we predicted. Every textbook chapter on the early universe is currently being rewritten in real time. We are living through a period of scientific revolution, where the data is moving faster than the theories can keep up. As you contemplate this cosmic mystery, imagine the astronomers sitting in the control rooms, looking at the data screens and seeing these bright, distant lights. They are sky archaeologists, and they are looking at something that challenges their very sense of reality. The universe is revealing itself to be a place of incredible efficiency and hidden depth. The light that carries the image of these impossible galaxies has traveled through 13 billion years of silence, just to tell us that we don't know as much as we thought we did. There is a strange comfort in this mystery. It reminds us that the universe is still capable of surprising us, that there are still frontiers to be explored and secrets to be unraveled. The smartphones in the Roman ruins are a call to curiosity, a reminder that the history of the cosmos is far more grand and far more mysterious than the stories we have been telling ourselves for the last 100 years. We are now standing at the beginning of a new era of discovery, looking through a golden mirror at a past that is more vivid and more complex than we ever dared to dream. The universe does not always make intuitive sense. As we move deeper into the revelations of the James Webb Telescope, we find ourselves at a point where the very nature of space and distance begins to warp. To understand the true scale of what we are seeing, we must confront a mathematical reality that seems to defy the laws of logic. Light travels at the ultimate speed limit of the universe, 186,000 miles per second. Nothing in the known cosmos can move faster than this. It is a constant confirmed by every measurement we have ever made. In a single year, light covers approximately 6 trillion miles. If we multiply that distance by the age of the universe, 13.8 billion years, simple arithmetic would suggest that the farthest thing we could ever see should be 13.8 billion light-years away. It's a logical conclusion, yet it is completely and utterly wrong. The actual edge of the observable universe sits 46.5 billion light-years away in every direction. We live inside a sphere of space nearly 7 times wider than the distance light could have traveled in the time since the Big Bang began. This is the great paradox of the expanding balloon of reality. This discrepancy is not a mistake in our calculations, but a result of the fact that space itself is stretching. To visualize this, imagine a balloon being slowly inflated. If you were to draw 2 dots on the surface of that balloon and watch them move apart, you might assume they are traveling across the rubber. But they are not. The dots are stationary relative to the surface. It is the surface between them that is growing larger. Space works the same way. Galaxies are not flying through space away from us like shrapnel from an explosion. Instead, the space between the galaxies is expanding, carrying them along like corks on the surface of a rising ocean. When a distant galaxy emitted the light we see today, 13.5 billion years ago, it was much closer to us than it is now. However, while that light was struggling to reach our telescopes, the universe continued to inflate. By the time those ancient photons finally arrived at Webb's golden mirrors, the galaxy that sent them had drifted to a current distance of over 46 billion light-years. Think of this journey like running on a treadmill towards someone standing at the far end of the room. As you run forward, the treadmill pulls you backward. You might eventually reach the other side, but by the time you do, you will have covered much more distance than the original length of the room would suggest. Light is fighting against this cosmic expansion every second of its journey. This creates a deeply strange reality where the universe is simultaneously finite in what we can observe and infinite in what actually exists. Beyond the 46.5 billion light-year boundary of our observable sphere, the universe continues. We know it is there because space extends indefinitely in every direction. Beyond that horizon, galaxies are shining, stars are exploding, and planets are orbiting their suns. We simply cannot see them because their light has not had enough time to fight through the expanding space to reach us. In fact, because the expansion of the universe is accelerating, that light may never reach us. We are living in a pocket of visibility that is slowly being isolated from the rest of the infinite cosmos. The force driving this expansion is something scientists call dark energy, a mysterious property of space itself that makes up 68% of everything that exists. Dark energy is unlike matter or radiation. It does not get diluted as the universe grows. If you have a box of gas and you double the size of the box, the gas becomes less dense. But dark energy remains a constant density. This means that as the universe creates more space, it also creates more dark energy, which in turn pushes the universe to expand even faster. It is a self-reinforcing loop that is stretching the fabric of reality at an ever-increasing rate. Every second, the edge of what we can see grows slightly larger as more light finally completes its journey. But the space itself is growing even faster. We are in a race against the stretching of the void, and eventually the expansion will win. This leads to a haunting realization about our place in time. We are fortunate to live in an era where the light from distant galaxies can still reach us. If we were to wait trillions of years, the expansion would become so great that every galaxy outside of our immediate neighborhood would be pushed beyond the cosmic horizon. Future astronomers living in our galaxy would look out into a sky that appears completely empty, a dark and lonely void with no evidence that other galaxies ever existed. They would have no way to measure the Big Bang or the expansion of space because the clues, the distant light fossils, would have vanished forever. Our current view of the 93 billion light-year diameter of the universe is a temporary privilege, a window into a scale of reality that is destined to disappear into the stretching darkness. As you consider the expanding balloon of reality, let the scale of it settle over you like a heavy, quiet blanket. The universe is not just a place where things happen, it is a dynamic, growing entity that is constantly reshaping the distances between us. The light that Webb captures is a bridge across this growing gap, a thin thread of connection to a past that is receding from us at millions of miles per hour. We are standing on a tiny point of reference, watching as the rest of existence inflates away from us. It reminds us that our perspective is limited by the physics of time and the geometry of space. What we call the universe is merely the part we are allowed to see, a small bubble of light in an infinite ocean of stretching shadow. This realization does not make us insignificant. Rather, it makes our ability to understand and measure these vast distances even more remarkable. We have found a way to map the inflation of the cosmos from the surface of a single small world, turning the mystery of the expanding balloon into a blueprint for the history of time itself. The James Webb Telescope is our most sensitive tool for measuring this inflation. By looking at how much the light from distant galaxies has been stretched, its redshift, we can calculate exactly how much the universe has grown since that light began its journey. Each galaxy is a marker on the cosmic balloon, a point of reference that allows us to track the heartbeat of the universe's expansion. We are seeing the universe grow in real time, witnessing the relentless push of dark energy as it expands the boundaries of our reality. The scale is staggering, the physics are mind-bending, but the story is one of persistent discovery. We are learning to navigate a universe that refuses to stay still, finding our way through a 93 billion light-year expanse that is getting larger with every breath we take. This is the nature of the cosmos, a vast, beautiful, and ever-expanding mystery that we are only just beginning to truly see. In the silence of the deep cosmos, the James Webb Space Telescope performed a task that was once thought to be an impossibility of observation. It stared at a single narrow patch of the sky, an area slightly larger than 3 full moons, and held its gaze for over 250 hours. The legendary Hubble Space Telescope had surveyed this region, known to astronomers as the Cosmos Webb Field, before. In that same patch of darkness, Hubble had identified roughly 10,000 galaxies, a number that seemed to represent a complete and exhaustive census of that part of the sky. Scientists believed they had seen the full depth of what that region had to offer. They were wrong by a factor of 80. When the Webb telescope's infrared eyes finally processed the data, the final count was staggering. Within that small frame of deep space, there were 797,942 distinct galaxies. Nearly 800,000 unique collections of stars, gas, and mystery were hiding in a shadow that we once thought was empty. To understand the scale of this census is to recognize that we have completely underestimated the population of the universe. This single photograph was not a simple snapshot. It was a masterpiece of technological endurance, created by combining more than 10,000 individual exposures. Each exposure was carefully aligned and corrected for the subtle errors that occur when observing from 1 million miles away. If you were to print the original Hubble Deep Field on a standard sheet of paper, the Webb version of this census would need to be printed on a mural 13 feet tall and 13 feet wide, just to maintain the same level of detail. It is a wall of cosmic history, where every tiny speck of light represents an entire galaxy containing billions or trillions of suns. This census has transformed our map of the universe from a sparse collection of known objects into a crowded, bustling metropolis of light. Each of the 800,000 galaxies in this image tells a specific story about the evolution of time. Some of these structures formed 12 billion years ago, during the chaotic and violent youth of the universe when galaxies were constantly colliding and merging. Others are relatively new, taking shape only a few billion years ago as the universe became more settled and organized. Because Webb can see in the infrared, it was able to capture the data for each of these galaxies simultaneously, measuring their distance, their brightness, their total mass, and the rate at which they are currently giving birth to new stars. This catalog allows scientists to track the biography of the cosmos across 98% of its history. We are no longer looking at isolated events, we are looking at the continuous flow of existence, watching how matter organizes itself over the eons. What makes this census truly revolutionary is not just the sheer number of galaxies detected, but the way they are distributed across the void. As astronomers analyzed the positions of these 800,000 worlds, they realized that the galaxies were not scattered at random, like grains of sand dropped on a floor. Instead, they appear to follow a precise and hauntingly beautiful pattern. They cluster along invisible threads, gather at massive intersections, and avoid certain empty regions entirely. This pattern is the visible signature of the cosmic web, the large-scale architecture of the universe. The galaxies are like the lights of distant cities viewed from an airplane at night, tracing the paths of invisible highways. In this case, the highways are made of dark matter, an invisible substance that provides the gravitational scaffolding for everything we see. Before this census was conducted, astronomers predicted that galaxies would become much rarer as we looked further back in time. They estimated that galaxies forming within the first 500 million years would be incredibly difficult to find, perhaps appearing as a few dozen scattered points in a survey of this size. The actual count exceeded those predictions by a factor of 10. Hundreds of extremely distant galaxies crowded into a cosmic era that our models said should have been nearly empty. This is the central mystery that the census has provided. The early universe was far more populated, far more active, and far more efficient at creating structure than anyone had predicted. The darkness of the ancient past was teeming with life-bearing potential, filled with massive galaxies that seemed to have appeared out of nowhere. Democratizing this data is perhaps its most profound legacy. When the team at the Whispering Scientist and other global researchers finalized this catalog, they released everything to the public: the images, the measurements, and an interactive viewer that allows anyone to explore these random patches of deep space. It means that a student in a classroom or a curious observer in the middle of the night can mine this information for their own discovery. We are all now part of this cosmic census. We can look at a tiny point of light in the corner of a digital map and realize that we are seeing a collection of 100 billion stars that no human eye had ever perceived until this moment. There is a deep, quiet comfort in the realization that the universe is so much more crowded than we thought. For every star we can see in our own night sky, there are millions of entire galaxies hidden in the folds of time. This census of 800,000 worlds is a reminder that we are part of a vast and interconnected community of matter. The light from these galaxies has traveled across the expanding balloon of reality, through the voids and along the filaments, just to be counted by a golden mirror in the 21st century. As we study the physical parameters of these galaxies, their morphology, their redshift, and their stellar ages, we are essentially reading the ledger of creation. We are seeing how the universe built itself, one galaxy at a time, across a 93 billion light-year expanse. As you consider the weight of these numbers, Let your mind rest on the sheer scale of the census. 800,000 galaxies in one small patch of sky. If we were to survey the entire sky with this level of detail, the number of galaxies in the observable universe would climb into the trillions. Space is not a lonely place, it is an overflowing reservoir of stars and planets. We are simply one small part of a much larger story, a single entry in a census that stretches back to the beginning of time. This discovery doesn't make us small, it makes us part of something infinitely more grand. The James Webb Telescope has shown us that whenever we think we have seen the limit of the universe, we need only look a little deeper into the darkness to find another 800,000 reasons to wonder. The universe is not a chaotic scattering of stars and gas, but a highly organized and interconnected structure that resembles a vast celestial nervous system. This is the cosmic web, the largest architectural feature in existence, stretching across the entirety of the 93 billion light-year expanse. When the James Webb Space Telescope conducted its massive census of galaxies, it revealed that these islands of light do not float freely in a void. Instead, they are tethered to invisible threads that dictate their motion and their destiny. These threads are the filaments of the cosmic web, and they represent the ultimate scaffolding of reality. To understand these filaments is to understand the secret logic of the universe, for they are the highways along which all matter travels, guided by a force that we cannot see but can measure with haunting precision. Most of the universe is composed of dark matter, a substance that does not emit, absorb, or reflect light. It is invisible to every traditional telescope, yet it comprises 85% of all matter in the cosmos. In the very first moments after the Big Bang, dark matter began to clump together due to tiny fluctuations in density. These clumps grew into long, thin strings and massive nodes, creating a network that spans the void. This is the invisible web. Normal matter, the gas and dust that eventually becomes stars and people, is drawn into these gravitational channels. It flows like water down a mountain, collecting in the valleys created by dark matter's gravity. The galaxies we see are merely the decoration on this invisible monument. They are the bright pearls strung along a necklace of shadow. Without these filaments, the universe would have remained a smooth, featureless fog of gas, never collapsing into the clusters and superclusters that define our night sky. The filaments themselves are tens of millions of light-years long, connecting the massive intersections where thousands of galaxies gather. These intersections are known as nodes, the busiest cities in the cosmic landscape. Between these filaments lie the voids, immense regions of emptiness where almost nothing exists. The contrast is extreme. Matter is pulled out of the voids and concentrated onto the filaments, making the web increasingly structured over time. As the James Webb Telescope peers into the infrared, it captures the glow of galaxies that are currently navigating these dark matter highways. We can see them lining up in specific directions, tracing the geometry of the filaments with their positions. It is a three-dimensional map of the invisible, allowing us to see the shape of the dark matter scaffold. By observing where the luminous matter has settled, recent observations have allowed us to detect the dark matter within these filaments directly for the first time. Using a phenomenon called gravitational lensing, astronomers can observe how a filament's gravity bends light from even more distant objects behind it. Just as a lens distorts an image, the concentrated mass of a dark matter thread warps the background galaxies, stretching them into subtle arcs. By measuring these distortions, we have confirmed that dark matter really does line the paths between galaxy clusters. We have even seen dark matter hanging from the terminal segments of the web, the thin, delicate threads that connect individual galaxies to the larger network. This confirmation proves that the cosmic web is not just a theoretical model, but a physical reality that binds the universe into a single, interconnected whole. The scale of these filaments is nearly impossible to visualize. Our own home, the Milky Way, is situated on a filament that connects us to the Virgo cluster and the Fornax cluster. This local thread stretches for approximately 110 million light-years. Light from the far end of our local structure began its journey toward us when the first dinosaurs were beginning to walk on Earth. We are part of a cosmic neighborhood that is vastly larger than our galaxy, yet it is only one small segment of the global web. The Webb pervades every corner of the observable universe, integrating every gravitationally bound structure into one network. Every galaxy you see in the Webb census is a passenger on one of these filaments, drifting slowly toward the nodes where the most massive concentrations of matter lie. As galaxies travel along these filaments, they undergo dramatic transformations. The filaments act as feeding tubes, funneling fresh hydrogen gas into galaxies to fuel the birth of new stars. However, these highways are also crowded. As galaxies move toward the intersections, they frequently interact with one another. They collide, they merge, and they are stripped of their gas by the hot plasma that fills the space between them. The environmental effects of living on a filament are what shape the diversity of the galactic population. A lonely galaxy in a void might remain a pristine spiral for billions of years, while a galaxy on a busy filament is likely to be battered and transformed into a red, starless elliptical. The cosmic web is both a creator and a destroyer, providing the raw materials for life while also creating the conditions that eventually bring star formation to a halt. There is a deep unity in the discovery of these filaments. It suggests that nothing in the universe exists in isolation. Every atom in your body was once part of a gas cloud that flowed along a dark matter filament to reach the young Milky Way. We are the products of a system that has been organizing itself for 13.8 billion years, moving matter from the vast emptiness of the voids into the dense, vibrant threads of the web. The James Webb Telescope is our first true window into the details of this process, showing us how the first filaments formed in the aftermath of the Big Bang, and how they have evolved into the complex network we see today. The census of 800,000 galaxies was the first step. Mapping the filaments that connect them is the second, deeper layer of our understanding. As you contemplate the filaments of the invisible web, let yourself feel the connection between all things. The universe is not a series of disconnected objects, but a living, breathing structure held together by the gravity of the unknown. We are standing on a tiny point of light within a web that spans 93 billion light-years, watching as the invisible threads guide the light toward our mirrors. The cosmic web is the ultimate proof of the universe's order, a masterpiece of architectural gravity that ensures that no star is ever truly alone. We are all travelers on these filaments, moving through a history that is written in the shadows and illuminated by the galaxies we are only just beginning to count. The standard model of cosmology makes clear and steady predictions about the early universe. According to these established theories, the period following the Big Bang was one of gradual cooling and slow assembly. About 380,000 years after the beginning, the first atoms formed, and another few 100 million years passed before the first stars ignited. These stars were expected to gather slowly into the first galaxies, a process that should have been modest and predictable. Galaxies in the first 500 million years were theorized to be rare, small, and dim, simple structures that hadn't yet had the time to build anything elaborate. However, the James Webb Space Telescope's observations have fundamentally contradicted his timeline. Within the first 400 million years, the cosmos was already producing an enormous, unexpected amount of light. Bright galaxies were already blazing across space, and massive structures had already assembled. This is what scientists now call the too much light, too early problem. Evidence of this discrepancy is not subtle. Multiple independent surveys have confirmed the same result using different instruments on the telescope. The early universe was significantly brighter than it should have been given the time available for galaxy formation. Researchers have calculated the total amount of light produced by all galaxies in the first billion years and compared it to theoretical predictions. The results are startling. The observed light exceeds the predictions by factors of 2 to 10, depending on the specific cosmic epoch examined. Finding 10 times more light than expected is not a minor error in measurement. It is a fundamental challenge to our understanding of how galaxies form and evolve. It suggests that the early universe was far more efficient at producing stars and structures than the modern universe is today. Several fascinating explanations have been proposed to solve this mystery. One possibility involves what astronomers call the initial mass function, which is the mathematical description of how stellar masses are distributed when stars are born. In the modern universe, Star formation produces a vast majority of small stars and only a few massive ones. However, it is possible that early star formation favored the creation of massive stars. These giants burn much hotter and brighter than smaller stars, so a galaxy filled with them would produce a much greater total light output. Another possibility involves star formation efficiency. Today, only a tiny fraction of available gas in a galaxy actually becomes stars. Most of it is heated or blown away. In the early universe, environmental conditions, such as the higher density of space, might have allowed gas to convert into stars with much greater efficiency, creating more light from the same amount of raw material. Supermassive black holes might also be playing a key role in this extra glow. When a black hole at the center of a galaxy consumes matter, the friction and gravity create an active galactic nucleus that can outshine all the stars in the galaxy combined. If these black holes were more common or more active in the infant universe than we previously thought, they could account for much of the excess light Webb is detecting. Recent data supports this idea, showing that many of these early bright galaxies do indeed harbor extremely luminous central engines. Each new discovery seems to push the boundary of this problem even earlier in time. Webb found bright galaxies at 600 million years, then 500, then 400, and now even 300 million years. Every time we look further back, we find that the universe was already busy and brilliant. The standard cosmological model is not completely broken, as it still accurately predicts many other things, like the cosmic microwave background and the distribution of elements, but it clearly misses something critical about how the first galaxies were built. Resolving this might require us to look at new physics. Perhaps dark matter behaves differently than we assumed in high-density environments, or perhaps star formation proceeds through mechanisms we haven't yet discovered. It is even possible that the initial conditions immediately following the Big Bang were more complex than our current simulations capture. What remains certain is that the universe's infancy was far more active, energetic, and bright than any scientist predicted. The light we see from that era has traveled across nearly 93 billion light-years of expanding space to tell us that the story of the beginning is much more magnificent than we ever imagined. As you settle into the quiet realization of this mystery, imagine the first billion years of time. Instead of a dark and empty void slowly flickering to life, it was a place of sudden and intense brilliance. The dawn was not a gentle rising of light, but a frantic and beautiful explosion of structure. We are the observers of a history that is being rewritten in real time, watching as a golden mirror 1 million miles away captures the glow of a past that refuses to stay simple. This extra light is a gift to our curiosity, a signal from the deep past that there is still so much more to learn about the origins of our reality. The too much light, too early problem is not just a scientific puzzle. It is a reminder that the universe is always more vibrant and surprising than the theories we use to describe it. In the profound silence of the deep cosmos, the James Webb Space Telescope has encountered a group of objects so paradoxical that they have earned the title of universe breakers. These are not merely distant lights. They are 6 gargantuan galaxies that existed when the universe was only 3% of its current age. According to every established law of cosmology, these objects should not be possible. They are mature, massive, and crowded with stars at a time when the universe should have contained only tiny, fragile seeds of galaxies. Finding them is the equivalent of peering into a nursery and discovering a group of infants with the physical stature and complexity of fully grown adults. They have shattered our understanding of the timeline of creation, suggesting that the early universe was capable of organizing itself with a speed and efficiency that defies our most advanced supercomputer simulations. The problem is the amount of mass these galaxies contain. Initial data suggests that some of these objects possess as many stars as our own Milky Way, yet they reached this stage within just 500 to 700 million years after the Big Bang. For perspective, the Milky Way has had over 13 billion years to grow and evolve into its current form. To achieve the same level of maturity in such a fraction of time, these early galaxies would have had to form stars at a rate hundreds of times faster than anything we observe in the modern universe. They appear as fuzzy dots of intense red light in Webb's infrared detectors, a color that signals both their extreme distance and their dense populations of old stars. Scientists were so stunned by these whoppers that many initially believed the data was a mistake, a calibration error, or a trick of the light. But as more observations come in, the reality of these universe breakers is becoming harder to ignore. The existence of these behemoths challenges the very foundation of the standard model of cosmology, known as lambda-cold dark matter. This model predicts a bottom-up approach to the universe, where small clumps of matter slowly merge over billions of years to form larger structures. The universe breakers suggest a much more top-down or accelerated process. It is as if the cosmic construction crew skipped the foundation and the framing, jumping straight to the finished skyscraper. If these galaxies are truly as massive as they appear, then the dark matter halos that host them must have also formed much faster than our theories allow. This would mean that the early density fluctuations in the aftermath of the Big Bang were much more extreme than the cosmic microwave background suggests, or that there is a fundamental piece of physics involving dark matter that we are completely missing. However, as we sigh, in this state of scientific crisis, some researchers are looking for more prosaic explanations that might save our understanding of the universe. One intriguing possibility is that these objects are not actually massive galaxies full of stars, but a new type of object entirely. They might be little red dots, highly compact regions powered by supermassive black holes. When a black hole at the center of a primordial galaxy consumes gas at a ferocious rate, it creates a surrounding disk of superheated material that glows with an intensity that can mimic the light of 100 billion stars. If this is the case, the universe breakers might not be heavy in terms of stars, but bright because of their central engines. This would mean the galaxies aren't actually breaking the universe, they are just hiding a monster in their hearts that makes them look much larger than they really are. Even with these potential explanations, a significant discrepancy remains. Webb continues to find roughly twice as many massive galaxies in the early universe as the standard model predicts. This has led to the theory of bursty star formation. In the high-density environment of the young cosmos, galaxies may not have grown at a steady, slow pace. Instead, they might have experienced sudden, violent bursts of star birth, followed by quiet periods. If Webb happened to catch a series of galaxies during their most intense growth spurts, they would appear much more massive and luminous than their average state would suggest. It is a game of cosmic timing, where we are witnessing the most dramatic moments of a galaxy's life rather than its everyday existence. There is also the possibility of monster stars or dark stars inhabiting these early structures. These are theoretical giants, thousands of times more massive than our Sun, which could have formed from clouds of pure hydrogen and helium. If the first generation of stars were these primordial monsters, they would produce an immense amount of light with relatively little total mass. This could trick our telescopes into seeing a massive galaxy when we are actually seeing a sparse collection of incredibly bright individuals. Whether it is black holes, bursty star birth, or monster stars, the universe breakers have forced us to acknowledge that the dawn of time was a far more complex and efficient factory of light than we ever dared to dream. As you contemplate these cosmic anomalies, let the mystery of the universe breakers remind you that our knowledge is always a work in progress. We build these magnificent tools like the James Webb Telescope specifically to find the things that don't fit our theories, because it is in those gaps that the greatest discoveries are made. These 6 impossible galaxies are a call to rethink the rules of the game, a reminder that the universe has secrets that it only reveals when we are brave enough to look deeper into the darkness. We are the detectives of the deep past, sifting through the infrared fossils of a time when the rules were being written in the fires of the first stars. The universe breakers may upend our cosmology, but in doing so, they lead us closer to the true story of how everything we see and everything we are came to be. In the velvet shadows of the infant universe, a population of titans began to stir, far sooner than any laws of traditional physics should have allowed. These are the supermassive black holes, the gravitational monsters that sit at the heart of the earliest galaxies discovered by the James Webb Space Telescope. To understand the scale of this mystery, we must first look at how a black hole is supposed to grow. In the modern cosmos, a black hole begins its life as a star, perhaps 20 or 30 times the mass of our Sun. When that star exhausts its nuclear fuel, it collapses under its own weight, crushing matter into a point of infinite density. From there, it must feed, pulling in gas, dust, and the occasional stray star, growing slowly and incrementally over billions of years until it reaches 1,000,000 or 1,000,000,000 times the mass of our Sun. This is a process of patient accumulation, a cosmic marathon that requires vast stretches of time to complete. But Webb has found these monsters already fully grown, lurking in galaxies that existed when the universe was less than 500 million years old. They did not have billions of years to grow, they barely had a few hundred million. They are the monsters in the infant darkness, and their existence suggests that the seeds of the universe were much larger than we ever imagined. One of the most perplexing examples is the black hole at the center of the galaxy, known as GNZ11. This galaxy is one of the most distant ever observed, appearing to us as it was just 430 million years after the Big Bang. When scientists pointed Webb's spectrograph at this ancient light, they detected a signature that was unmistakable, extremely dense gas swirling at incredible speeds. This is the telltale fingerprint of a black hole actively feeding, pulling matter inward with such ferocity that the gas heats up and glows with a light that outshines the stars surrounding it. The mass of this black hole is estimated to be millions of times that of our Sun. To reach such a staggering size in such a short amount of time is theoretically impossible if it started as a normal star. Even if it began feeding the very moment it was born and consumed material at the absolute maximum speed allowed by the laws of physics, a limit known as the Eddington limit, it still could not have reached this mass by such an early date. The math simply does not add up, leaving astronomers to search for a new origin story for these primordial giants. Several theories are now emerging to explain how these monsters could have gotten such a head start. One possibility involves the concept of direct collapse black holes. In the dense, high-pressure environment of the early universe, it is theorized that massive clouds of hydrogen gas might have collapsed directly into black holes without ever forming stars first. Imagine a cloud containing 100,000 times the mass of our Sun suddenly succumbing to gravity and skipping the entire stellar life cycle, crushing itself instantly into a massive gravitational seed. This would give the black hole a massive advantage, allowing it to start its life as a giant rather than a small stellar remnant. While this process has never been observed in the modern universe, the conditions of the infant darkness were unique, and mathematical models suggest it was a viable path for creating the titans that Webb is now uncovering. Another intriguing theory involves the existence of dark stars. These are not black holes, but theoretical objects powered by the annihilation of dark matter rather than nuclear fusion. These stars could have grown to be millions of miles wide and millions of times more massive than our Sun, burning with a cool but immense light. Eventually, when their dark matter fuel was exhausted, these behemoths would collapse, leaving behind a ready-made supermassive black hole. Whether it was through direct collapse or the death of dark stars, it is clear that the infant universe was a place where gravity worked on a scale we are only beginning to comprehend. The darkness was not a quiet void, it was a nursery for giants, a place where the rules of growth were rewritten by the extreme density of the newborn cosmos. The presence of these black holes is not just a curiosity, it is a fundamental part of how galaxies themselves evolved. A supermassive black hole is not a passive resident of a galaxy, it is its regulator. As matter spirals into the black holes more, it releases an incredible amount of energy in the form of radiation and powerful jets of particles. This energy can act as a cosmic thermostat. It can heat the surrounding gas, preventing it from cooling and forming new stars, effectively shutting down the galaxy's growth. Conversely, the shock waves from these jets can compress gas clouds and trigger a sudden burst of star formation. Finding these monsters so early means that they were influencing the development of the first galaxies from the very beginning. They were the architects of the cosmic structures we see today, shaping the distribution of stars and the chemical composition of the space around them, the disk of. Theory of these early black holes also provides a clue into the reionization of the universe. During this era, the neutral hydrogen gas that filled space was stripped of its electrons, making the universe transparent to light. While we once believed that the first stars were solely responsible for this transformation, the discovery of so many active feeding black holes suggests they played a major role. The intense ultraviolet radiation and X-rays pouring off these early monsters would have acted like cosmic blowtorches, clearing the fog of the Dark Ages and allowing the first light to travel across the vast distances Webb is now surveying. The monsters were not just consumers of matter, they were the engines that helped clear the path for the future of the universe. As you consider these monsters in the infant darkness, let the scale of their power settle into your mind. We are looking at objects that defy our understanding of time and growth, giants that emerged from the shadows of the Big Bang fully formed and hungry. They remind us that the history of the universe is not always a slow, steady progression, but a story of sudden leaps and hidden processes. The light Webb captures from these ancient feeding frenzies is a bridge to a time when gravity was king and the first structures were being forged in the heat of the primordial void. We are the observers of a time when the universe was small, dense, and dominated by monsters that would eventually become the quiet, invisible anchors of the galaxies we live in today. The infant darkness was never empty. It was a realm of titans, and through the golden eye of Webb, we are finally seeing them for what they truly were. In the deep, ancient silence of the primordial universe, long before the first modern stars began to shine, there lived a generation of giants that the world has never seen since. These were the Populati. On 3 stars, the very first sources of light to flicker into existence within the vast, hydrogen-filled darkness. According to our most advanced theoretical models, these stars were unlike anything in our current neighborhood, because the early universe was composed almost entirely of hydrogen and helium, without any of the heavier elements that help gas clouds cool and fragment today. These first stars could grow to gargantuan proportions. They were the primordial monsters, weighing thousands or even tens of thousands of times more than our Sun. They burned with a fierce, violet-white intensity, consuming their fuel at a terrifying rate. While a star like our Sun might live for 10 billion years, these giants lived and died in a mere few million, a heartbeat in cosmic time. For decades, these stars remained a mathematical ghost, a prediction of what must have been, but with no physical proof of their existence. Now, the James Webb Space Telescope has detected a chemical fingerprint in the light of a distant galaxy that finally confirms their presence in the infant darkness. This fingerprint was found within the spectrum of a galaxy labeled GS 3073. When scientists split the light of this galaxy into its component colors, they found something truly bizarre, an extreme imbalance of nitrogen compared to oxygen. In the modern universe, the ratio of these elements follows a predictable pattern based on how stars live and die. But in this ancient galaxy, nitrogen levels were almost double what they should have been for any normal population of stars. This specific chemical signature is exactly what models predicted would be produced by the first generation of monster stars. These giants, powered by their immense gravity, would have utilized the carbon-nitrogen-oxygen cycle with a ferocity impossible in smaller stars. They would have spewed vast quantities of nitrogen-rich material into space through powerful stellar winds before they finally collapsed. What Webb has found is the lingering evidence of these winds, a chemical ghost left behind by giants that died billions of years before the Earth was even a thought. The existence of these primordial giants provides a missing piece to the puzzle of the early universe. We have long struggled to explain how the first supermassive black holes could have become so large so quickly. If the first stars were these monsters, they would have left behind massive black hole seeds when they died, seeds that already weighed thousands of solar masses. This would have given the gravitational monsters we see today a significant head start, allowing them to reach supermassive status in a fraction of the time. These stars were also the primary architects of reionization. Their intense ultraviolet radiation would have been powerful enough to strip electrons from the hydrogen atoms filling the void, effectively turning the universe from an opaque fog into the clear, transparent medium we observe today. They were the lanterns of the deep past, burning briefly but brilliantly enough to change the state of the entire cosmos forever. But perhaps the most profound impact of these primordial giants is their role in creating the elements that make up our world. Every atom of oxygen you breathe, the carbon in your DNA, and the nitrogen in the soil was once forged inside the nuclear furnace of a star. In the early universe, these elements did not exist. There was only the simple, pristine gas left over from the Big Bang. The monster stars were the first factories of complexity. They took the simplest building blocks of the universe and crushed them together to create the first heavy elements. When they died, they scattered these seeds into the surrounding space, polluting the pristine gas and allowing the next ration of stars to form with different properties. Without these first giants, the universe would have remained a simple two-element void. We owe our existence to a generation of stars that were destined to live fast and die young, leaving their chemical fingerprints as the only evidence of their brief but essential lives. As we look at the data from Webb, we are seeing the transition from a universe of simplicity to a universe of complexity. The detection of nitrogen in GS 3073 is more than just a chemical measurement. It is a confirmation that the story we have told ourselves about the early universe is fundamentally correct in its outlines, even if the scale is more extreme than we imagined. These monster stars were the brief, essential bridge between the Big Bang and the universe of galaxies we see today. They were the first to challenge the darkness, and their legacy is carried in every heavy atom in the cosmos. By finding their signature, we are finally connecting the dots of our own lineage, tracing the path from the first hydrogen clouds to the complex chemistry of life. The scale of these stars is almost impossible to grasp. If you were to place one of these primordial giants in the center of our solar system, it would extend far beyond the orbit of Jupiter. Its light would be so intense that it would vaporize any planet in its vicinity instantly. Yet, because they formed in a universe that was much denser and hotter than our own, they were the stable, natural outcome of their environment. They represent a phase of cosmic history that has ended forever. The conditions required to create such monsters no longer exist in the modern, expanded universe. We are looking at a unique era of giants, a time when the universe was small enough and raw enough to produce individuals of staggering power. As you consider the chemical fingerprint left by these giants, let a sense of deep time wash over you. The light we are analyzing has been traveling for over 13 billion years, carrying the secret of these stars across the expanding balloon of reality. It has survived the stretching of space and the passage of eons just to tell us about the first creators. The primordial giants were the architects of the light, the first to break the silence of the infant darkness. Through the golden eye of Webb, we are finally hearing their story, whispered through the chemical signatures of a galaxy at the edge of time. They remind us that the universe is a place of constant transformation, where the death of the first stars provided the lifeblood for everything that followed. In the vast, silent reaches of the 93 billion light-year expanse, there is a hidden architecture that dictates the movement of every star and the shape of every galaxy. While we spend our lives observing the light emitted by luminous matter, the true masters of the universe's structure are the highways of dark matter. This mysterious substance, which neither emits nor reflects light, acts as the invisible skeleton of the cosmos. It makes up 85% of all matter in existence, and without its gravitational pull, the universe would be a featureless, chaotic mist of gas. The James Webb Space Telescope has not only confirmed the existence of this scaffolding, but has allowed us to witness how these invisible highways guide the flow of matter across the void. To understand dark matter is to realize that the galaxies we see are merely passengers on a much larger, darker journey, drifting along gravitational corridors that were established in the very first moments after the Big Bang. Dark matter provides the scaffolding for what we call the cosmic web. Imagine a vast, three-dimensional network of threads and intersections, like a spiderweb stretching across the entire observable universe. The threads of this web are the filaments, long and thin concentrations of dark matter that stretch for tens of millions of light-years. Where these filaments cross, they form massive nodes, the high-density regions where galaxy clusters reside. These filaments are effectively highways in space. Gravity acts as the engine, pulling normal gas and dust into these dark matter channels. Once trapped within a filament, the matter has no choice but to follow the path laid out for it, flowing toward the nodes like water streaming down the grooves of a mountain. We see galaxies lining up along these specific directions, tracing the geometry of the invisible highways with haunting accuracy. It is a masterpiece of architectural gravity that ensures the universe is not just a collection of random parts, but a single interconnected system. The scale of these highways is staggering to the human mind. Our own Milky Way sits on a filament that connects our local neighborhood to the massive Virgo cluster. This single thread of the cosmic web is over 100 million light-years long. If you could see dark matter, you would see a bridge of shadows stretching from our galaxy across a distance so vast that light takes an entire epoch of history to cross it. These highways are not static, they are dynamic and evolving. As the universe expands, the voids, the empty spaces between the filaments, grow larger, pushing the highways further apart. Simultaneously, the gravity within the filaments continues to pull more matter inward, making the highways denser and more defined over time. We are witnessing a cosmic struggle between the expansion of space and the attraction of dark matter, a process that has been refining the structure of the universe for 13.8 billion years. One of the most remarkable breakthroughs in modern astronomy is our ability to map these invisible highways directly. Because dark matter has mass, it warps the fabric of space-time around it. When light from an even more distant galaxy passes through a dark matter filament on its way to Earth, the light is bent and distorted. This effect, known as gravitational lensing, allows us to see the shadow of the dark matter. By measuring the subtle warping of thousands of background galaxies, scientists can reconstruct the shape and density of the filament that caused the distortion. Recently, researchers used the Subaru telescope in Hawaii and data from the James Webb Telescope to detect dark matter along the terminal segments of these highways for the first time. They observed dark matter hanging from the very ends of the filaments, where they connect to individual galaxies like the Coma cluster. This discovery confirms that dark matter is not just concentrated in big clumps, but genuinely pervades the entire network, creating a continuous and unbroken structure that spans the cosmos. These dark matter highways do more than just provide a path for galaxies, they act as the primary feeding tubes for the growth of the universe. Cold hydrogen gas flows along these filaments, funneling into galaxies to provide the raw materials for new star formation. Without this constant supply of fresh gas, galaxies would quickly use up their internal reservoirs and fade into darkness. However, these highways are also dangerous places. Because matter is so concentrated within the filaments, galaxies frequently encounter one another as they travel toward the nodes. These encounters lead to collisions, mergers, and the violent stripping of gas. The highways are busy, high-traffic corridors where the environment is constantly shaping and reshaping the objects within them. A galaxy's destiny is determined by which highway it inhabits and how many neighbors it must contain. First, it drifts toward the great clusters at the intersections. The realization that we are surrounded by an invisible network of highways changes how we perceive our place in the universe. We are not drifting aimlessly in an empty void. We are anchored to a structure that is far older and far larger than any star. Every atom of carbon in your body and every drop of water on Earth was once part of a gas cloud that navigated a dark matter filament to reach our corner of the galaxy. We are the beneficiaries of a system that organized the chaos of the Big Bang into the structured reality we inhabit today. The cosmic web is the ultimate evidence of order in the universe, a silent and eternal framework that connects the smallest moon to the largest supercluster. As you reflect on the highways of dark matter, Let the sense of their permanence settle over you. While stars will eventually burn out and galaxies will fade, the dark matter scaffolding will remain, holding the universe together with its invisible grip. The light we see through the James Webb Telescope is a guide, a way for us to trace the paths of these hidden corridors and understand the logic of the beginning. We are the observers of a vast, dark highway system that spans 93 billion light-years, watching as the light of 800,000 galaxies illuminates the path. It is a story of connection, of gravity, and of the persistent structure that underlies all of existence. We are travelers on a road we cannot see, moving through a history that is written in the gravity of the shadows and revealed by the golden mirror of our curiosity. In the profound depths of the early universe, where we expected to find only the chaotic and disorganized first steps of structure, the James Webb Space Telescope has uncovered a formation of such staggering proportions that it defies our understanding of cosmic timing. This structure is known as the cosmic vine, a massive bow-shaped chain of at least 20 closely packed galaxies that stretches more than 13 million light-years across the void. To find a structure of this scale appearing when the universe was only a few billion years old is a revelation that challenges the very limits of how fast gravity can organize space. If our own Milky Way galaxy, which measures about 100,000 light-years across, were a single grain of sand, the cosmic vine would be a long, sweeping thread nearly a football field in length. All 20 of these galaxies show a redshift indicating their light traveled for over 11 billion years to reach us. They represent an era when the universe was still in its adolescence, yet they have already assembled into a sophisticated, unified front that looks more like a modern supercluster than a primordial group. What makes the cosmic vine truly remarkable is not just its physical size, but the state of the galaxies that inhabit it. These are what astronomers call quiescent giants. In the early universe, most galaxies are frantic factories of star formation, blazing with the blue light of newborn suns and rich with the raw hydrogen gas needed to fuel future generations. They are vibrant, messy, and constantly growing. However, the two largest galaxies at the heart of the cosmic vine tell a different, more haunting story. When scientists analyzed the specific wavelengths of light these giants emitted, they found that the fires of star formation had almost completely gone out. These galaxies are dead, or at least they have entered a state of deep slumber. They have already used up their gas reserves and ceased the production of new stars, a process known as quenching. Finding such massive, dormant objects so early in the history of the cosmos is like discovering an ancient, weathered monument in a landscape that should still be covered in fresh volcanic ash. The existence of these quiescent giants in the middle of a massive structure like the cosmic vine suggests that the environment of the early universe was far more influential than we realized. There are several theories as to why these giants went quiet so soon. One possibility is the sheer violence of their birth. Because the cosmic vine is such a dense environment, these galaxies likely experienced frequent and powerful mergers. When two massive galaxies collide, they trigger an incredible frantic burst of star formation that can consume nearly all available gas in a very short period of time. This starburst is so intense that it can effectively starve the resulting galaxy, leaving it with billions of stars but no raw material to create more. Another possibility involves the invisible medium that fills the space between galaxies. As the cosmic vine gathered, it trapped hot plasma in its gravitational well. When a galaxy moves through this hot plasma at millions of miles per hour, it experiences a force called ram pressure. This pressure acts like a cosmic wind, stripping the cold gas right out of the galaxy as it plunges through the structure. This process of ram pressure stripping is a vivid reminder that the universe is not a gentle place. Imagine a runner holding a handful of dry sand while sprinting against a hurricane. Eventually, the wind will blow the sand away, leaving the runner's hands empty. In the same way, the cosmic vine is a structure that both creates and depletes. It draws galaxies together into a spectacular display of cosmic architecture, but the very act of bringing them together subjects them to forces that can prematurely end their productive lives. The cosmic vine is effectively a cluster in the making, a preview of the massive nodes that define the modern cosmic web. It is a work of art in progress, a 13 million light-year bow of light that is slowly collapsing into a single, unified cluster of thousands of galaxies. The quiescent giants at its center are the first to have completed their evolution, serving as silent omens of the fate that eventually awaits all dense regions of the universe. The discovery of the cosmic vine also provides a critical test for our simulations of dark matter. Since dark matter provides the gravitational scaffolding for the cosmic web, the existence of such a large and organized chain of galaxies so early in time tells us exactly how fast that scaffolding must have formed. If the cosmic vine is there, then the dark matter filament supporting it must be even larger and more robust. This pushes the timeline for the assembly of the large-scale structure of the universe significantly earlier than previous models allowed. We are finding that the universe did not wait to build its masterpieces. It began weaving the fabric of the cosmic web with a speed and intensity that suggests our understanding of dark matter's behavior in the early universe is still incomplete. The vine is a thread of evidence that connects the smooth, uniform aftermath of the Big Bang to the complex, clustered reality we see today. As you reflect on the scale of the cosmic vine and its sleeping giants, consider the silence of those dormant galaxies. Within them, billions of stars are still shining, orbiting their common centers of mass in a slow, graceful dance that will last for trillions of years. But the era of creation has ended for them. They have become stable, serene, and unmoving in a part of the universe that is otherwise filled with the chaos of birth. They are a reminder that even at the beginning of time, there were places where the work of building was already finished. The light from the cosmic vine has traveled through the expanding balloon of reality through the voids and across the filaments, to bring us this message from the deep past. It is a story of how gravity organizes the void, turning random fluctuations into magnificent structures that stretch across the sky. Through the golden eye of the James Webb Telescope, we are seeing the cosmic vine not just as a collection of distant dots, but as a living, evolving entity. We are witnessing the birth of a supercluster, the quenching of giants, and the power of the invisible highways that guide them. Every galaxy in that 13 million light-year chain is a testament to the persistent and structured nature of our universe. They are the landmarks of the early cosmos, guiding us toward a better understanding of how the 93 billion light-year expanse came to be. The cosmic vine is a bridge across time, showing us that the seeds of the modern universe were sown with a grandeur that we are only now beginning to truly appreciate. As we move from the crowded highways of the vine into the vast empty regions of the cosmos, the contrast only serves to highlight the incredible complexity of the structures that light and gravity have built together. In the vast and intricate architecture of the 93 billion light-year expanse, the most striking feature is not the brilliance of the galaxies, but the overwhelming presence of nothingness. Between the glowing filaments of the cosmic web and the crowded intersections of the cosmic vine stretch enormous, empty regions known as cosmic voids. These are the deserts of the universe, immense bubbles of space that contain almost no stars, almost no gas, and almost no matter of any kind. They represent the largest continuous volumes of emptiness in existence, some extending for hundreds of millions of light-years in every direction. If the cosmic web is the skeleton of the universe, then the voids are the hollow spaces within the bone, the vast expanses where the work of gravity seemingly failed to occur. To understand the true scale of the cosmos, one must look away from the light and confront these silent, dark interiors, for they hold the secret to how the universe's matter was partitioned in the first moments of time. Imagine standing in the absolute center of one of these voids. If you were to look out in any direction, your eyes would meet nothing but a terrifying and perfect darkness. In a normal region of space, like our own neighborhood, the night sky is peppered with the glow of nearby stars and the distant smudge of neighboring galaxies. But in the heart of a void, the nearest galaxy might be 50 or 100 million light-years away. The sky would be an empty black canvas, devoid of the landmarks that have guided human curiosity for millennia. These regions are so sparse that they contain less than 10% of the universe's average matter density. They are the ultimate isolation, cosmic deserts where the expansion of space has pushed everything away, leaving behind a vacuum that is as close to true nothingness as the physical world allows. These voids are not just empty, they are the negative space that defines the beauty of the structure surrounding them. The formation of these voids is a process that began with tiny, almost imperceptible differences in the density of the early universe. In the aftermath of the Big Bang, matter was spread nearly evenly, but not perfectly. Some regions were slightly denser than average, while others were slightly less dense. Gravity, the great sculptor of the cosmos, acted on these differences with relentless persistence. The denser regions had slightly more gravitational pull, drawing in matter from their surroundings. Conversely, the underdense regions had less gravity, and they began to lose their material to the stronger neighbors. Over billions of years, this process created a runaway effect. Matter flowed out of the underdense regions and accumulated on the boundaries, creating the thin, bright filaments of the cosmic web. The regions that lost their matter became larger and emptier, inflating into the massive bubbles we see today. The voids grew because they were the losers in the gravitational tug-of-war, stripped of their potential to build stars so that the filaments and clusters could thrive. The largest known void, often called the Boots Void or the Great Nothing, stretches approximately 330 million light-years across. It is a region so vast that if the Milky Way were located at its center, we would not have known other galaxies existed until the development of high-powered telescopes in the 20th century. Light takes over 300 million years just to cross this single pocket of emptiness. If you were to travel at the speed of light, you would spend millions of generations in total darkness before seeing a single star. Yet, despite their name, these voids are not strictly empty. A few small, lonely galaxies do drift through these deserts, isolated from the bustling traffic of the filaments. These void galaxies are fascinating to scientists because they have evolved in total solitude. Without the collisions, mergers, and gas-stripping forces of the dense clusters, these galaxies provide a pristine look at how a collection of stars grows when left entirely to its own devices. They are the survivalists of the cosmos, making do with the meager scraps of gas that remain in the desert. Scientists study these deserts because they provide the cleanest laboratories for understanding the expansion of the universe. In dense regions where galaxies are packed together, the local gravity of clusters complicates our mesoremense. Galaxies pull on each other, creating peculiar velocities that mask the true rate of the universe's growth. But in the heart of a void, local gravitational effects are almost non-existent. The few objects that live there move primarily under the influence of the global expansion of space. By measuring the motions of these lonely galaxies and the rate at which the voids themselves are growing, astronomers can get a direct reading on the strength of dark energy. The voids act like inflating balloons within the structure of the web, and the speed at which they push against the surrounding filaments tells us exactly how fast the fabric of reality is being stretched. The emptiness, it turns out, is one of our most powerful tools for measuring the weight of the entire universe. There is a haunting irony in the fact that the voids are growing larger every second because dark energy, the force driving the acceleration of the universe, is a property of space itself. The more space there is, the more dark energy exerts its influence. Since the voids contain the most space and the least matter to hold it back with gravity, they are the primary sites where expansion takes hold. The voids are pushing outward, compressing the filaments, and making the cosmic web even thinner and more defined. Trillions of years from now, the voids will have expanded so much that they will have pushed all the matter of the universe into tiny, isolated islands, separated by such vast distances of nothingness that no light will ever be able to cross the gap. The deserts are destined to win the long-term struggle for the cosmos, eventually consuming the structure that gravity works so hard to build. As you reflect on these deserts of the void, let the silence of the empty space settle over you. We often focus on the light because it is what we can see, but the story of the universe is just as Much a story of the gaps between the stars. We are residents of a filament, a busy highway of matter, looking out at the vast, dark oceans that surround us. The voids remind us that the 93 billion light-year expanse is mostly a place of quiet, undisturbed vacuum. They provide the contrast that makes the cosmic vine and the early galaxies seem so miraculous. In a universe that is mostly empty, the fact that matter managed to gather at all is a testament to the incredible power of gravity. The deserts are the background upon which the masterpiece of the cosmic web is painted, the deep, dark breaths of a universe that is still growing, still stretching, and still full of secrets hidden in the nothingness. Through the golden eye of the James Webb Telescope, we are learning to map these voids with the same precision we once reserved for the stars. We are finding that the shape, size, and distribution of these empty bubbles are the ultimate fingerprints of the Big Bang. They tell us how much dark matter exists and how the energy of the beginning was distributed. Every empty light-year is a piece of the puzzle, a silent witness to the laws of physics that govern the large-scale structure of reality. The deserts are not a failure of creation, they are a fundamental part of its design, the vast, open spaces that allow the web to exist in its magnificent, interconnected form. As we move from these dark interiors back toward the light, we carry with us a new appreciation for the scale of the void and the fragile, beautiful threads of matter that dare to cross it. In the profound silence of the cosmos, every beam of light is a storyteller, carrying secrets about its origin and the vast distances it has traveled to reach us. However, as we look deeper into the 93 billion light-year expanse, we realize that the light itself has undergone a dramatic transformatio. It has been physically altered by the very fabric of the universe it traverses. This phenomenon, known as the stretching of the spectrum or redshift, is the fundamental key that allows the James Webb Space Telescope to decode the history of the early universe. To understand this stretching is to understand that space is not a static stage where events occur, but a dynamic, expanding medium that interacts with everything moving through it. Every photon emitted by the first galaxies has had its wavelength pulled and lengthened by the relentless growth of the universe, shifting its identity from the vibrant blues and violets of its youth into the long, invisible whispers of infrared. When a massive star in a distant galaxy ignites, it releases a flood of high-energy ultraviolet and visible light. These photons begin their journey with short, tight wavelengths, vibrating with intense energy. But as these photons travel toward Earth, the space through which they move is expanding, because the light is coupled to the fabric of space-time. As the space stretches, the light waves stretch along with it. Think of a wave drawn on a piece of elastic. If you pull the ends of the elastic, the wave becomes longer and its peaks move further apart. By the time these ancient photons reach our solar system, their wavelengths have expanded by a factor of 14 to 16 times their original length. This is why we cannot see the most distant galaxies with our naked eyes, or even with traditional optical telescopes. Their light has been stretched so far that it has moved entirely out of the visible spectrum and into the infrared, a region of light that carries heat but remains invisible to the human eye. This stretching is not merely a distortion, it is a precise mathematical tool. Scientists measure this shift using a technique called spectroscopy, which involves splitting the AR, iving light into a rainbow-like pattern. Within this spectrum, atoms like hydrogen and oxygen leave behind specific markers, dark lines at very particular wavelengths. By observing how far these lines have shifted from their rest positions measured in a laboratory on Earth, astronomers can calculate exactly how much the universe has expanded since that light was emitted. This value, known as the redshift, tells us the age and distance of the object with staggering accuracy. A galaxy with a redshift of 14 is not just far away, it is a time capsule from an era when the universe was 15 times smaller than it is today. Every inch of space we walk through now was once a tiny fraction of its current size, and the stretched light is the only physical evidence of that more compact, energetic past. The James Webb Space Telescope was specifically engineered to be the master of this stretched spectrum, while its predecessor, the Hubble Space Telescope, captured the universe primarily in visible light. Webb focuses almost entirely on the infrared. It is equipped with mirrors coated in a microscopic layer of gold, a material chosen for its incredible ability to reflect these long-stretched wavelengths. By operating in the infrared, Webb can see through the thick clouds of cosmic dust that block visible light, but more importantly, it can catch the light that has been traveling for 13 billion years. The telescope's instruments, such as the near-infrared camera and the mid-infrared instrument, allow it to see light that has been stretched by factors ranging from 2 to more than 20. Without this specialized infrared vision, the most important chapters of cosmic history, the birth of the first stars and the assembly of the first galaxies, would remain forever hidden in the darkness of the unobservable past. There is a poetic beauty in the realization that the universe itself is responsible for the colors we see in the deep field images. The brilliant reds and deep oranges that dominate Webb's photographs are the visual representation of this stretching. They are the colors of extreme age and incredible distance. When we see a tiny crimson smudge in a Webb image, we are looking at a galaxy that was originally blazing with a fierce young blue light. The universe has acted as a giant lens and a time warper, cooling that light and stretching it until it became a ghostly infrared signal. It is a reminder that the further we look into the distance, the more the universe changes the information it sends us. We must learn to speak the language of the infrared if we want to hear the story of how the cosmos began. Stretching the spectrum also affects the perceived brightness of these distant worlds. As a wavelength stretches, its energy decreases. This means that high redshift galaxies appear much dimmer than they would if they were closer to us, not just because of the distance, but because the individual photons have lost energy during their long journey through expanding space. Additionally, because the universe is expanding, the rate at which photons arrive at the telescope is slowed down. This time dilation effect means that we see the processes in distant galaxies, like the explosion of a supernova, occurring in slow motion. The universe is not only stretching the light, it is stretching the very tempo of time as perceived from our distant vantage point. Every observation is a complex calculation of energy loss and temporal expansion, requiring the most sophisticated technology humanity has ever created. As you reflect on the stretching of the spectrum, let the sense of the universe's movement settle into your thoughts. We live in a reality that is constantly pulling at its own boundaries, a fabric that is never still. The HT reaching us today is a survivor of that pulling, a thin thread of energy that has been elongated across billions of light years. It is a miracle of physics that we can catch these weakened, stretched photons and reconstruct the image of a galaxy as it appeared at the dawn of time. The redshift is the heartbeat of the expanding balloon of reality, a constant reminder that the universe is growing, changing, and carrying us along with it. Through the golden mirror of Webb, we are finally able to see the entire spectrum of existence, moving beyond the limits of our biological vision to witness the true, stretched beauty of the beginning. The James Webb Telescope has revealed that our previous census of the universe was missing the most important participants. By following the stretched light, we have found hundreds of thousands of galaxies that were once invisible. We are finding that the dark ages were not as dark as we thought, but were instead filled with a light that simply required a different kind of eye to see. Every stretched wavelength is a bridge to a past that is receding from us, a connection to a history that is written in the very motion of space itself. As we move from the technical stretching of light to the deeper mysteries of how fast this expansion is actually happening, we realize that the spectrum is only the first layer of the puzzle. The light has been stretched, but the reason for that stretching and the speed at which it occurs remains one of the most significant tensions in modern science. In the quiet mathematical heart of cosmology, there exists a conflict that threatens to undo our entire understanding of the 93 billion light-year expanse. This conflict is known as the Hubble tension, and it is centered on a single vital number, the Hubble constant. This value represents the rate at which the universe is expanding today, the literal heartbeat of the cosmos. For decades, astronomers have sought to measure this number with absolute precision, believing that once we knew exactly how fast space was stretching, we could finally calculate the age of the universe and its ultimate fate. However, the more we measure, the more the universe seems to disagree with itself. We have arrived at a point where our two most reliable methods for measuring the expansion produce two different, incompatible results. It is a mystery that suggests either our measurements are flawed or, more excitingly, that there is a fundamental piece of new physics, a hidden force or an unknown particle, that we have yet to discover in the darkness. To understand the tension, we must look at the two ways we calculate the speed of the universe. The first method involves looking at the very beginning of time. Scientists study the cosmic microwave background, the faint, freezing afterglow of the Big Bang that permeates every inch of the sky. This radiation contains a pattern of tiny hot and cold spots that act as a blueprint for the early universe. By feeding this blueprint into our best cosmological models, we can predict exactly how fast the universe should be expanding today. This early universe method gives us a value of approximately 67 kilometers per second per megaparsec. It is a precise, elegant calculation that has been verified by multiple satellite missions. Yet it describes a universe that is expanding more slowly than what we actually see when we look out the window. The second method involves looking at the modern nearby universe. Astronomers measure the distances to local galaxies using standard candles, such as Cepheid variable stars and Type I, a supernovae. These objects have a known intrinsic brightness, allowing us to calculate their distance based on how faint they appear in our telescopes. By combining these distances with the redshift of the galaxies, we can measure the expansion rate directly. This late universe method consistently yields a value of approximately 73 kilometers per second per megaparsec. A gap of 6 kilometers might seem small in the context of the infinite void, but in the world of high-precision physics, it is a chasm. The discrepancy is statistically significant, meaning it is almost certainly not a fluke or a simple error in judgment. The early universe predicts one speed, the later universe demonstrates another. The tension is the sound of the universe's history failing to match its present. For years, some scientists hoped that the Hubble Space Telescope might have had a subtle calibration error that was causing this discrepancy. They believed that once we launched a more powerful observer, the numbers would finally align. But the James Webb Space Telescope has only deepened the mystery. In its first 2 years of operation, Webb has been used to remeasure these distances with unprecedented clarity. It looked at the same Cepheid stars and supernovae that Hubble observed, but with its superior infrared vision, it was able to see through the dust and interference that might have blurred previous results. The Webb data confirmed the higher value of 73. The late universe measurement is robust. The tension is real. We are officially living in a universe that is expanding faster than our best theories of its birth say it should be. This leaves us with a profound problem. If the math for the early universe is correct, and the measurements for the late universe are also correct, then something must have happened in the intervening 13 billion years that we do not understand. One possibility is that dark energy, the mysterious force pushing the universe apart, is not a constant. In Einstein's original equations, the cosmological constant describes dark energy as a steady, unchanging pressure. But what if dark energy evolves? If it has grown stronger over cosmic time, it would act like a foot pressing harder on the accelerator, causing the expansion to speed up beyond the initial predictions of the Big Bang. This would change everything we know about the future of the cosmos, suggesting that the expansion might eventually lead to a more violent conclusion than we anticipated. Another possibility involves the existence of early dark energy, or unknown primordial particles. Perhaps in the first few 100,000 years after the Big Bang, there was an additional force at work that gave the expansion a temporary boost before fading away. This would alter the blueprint of the cosmic microwave background in a way that our current models don't account for. There is also the chance that our understanding of gravity itself is incomplete. While general relativity has passed every test we have thrown at it within the solar system, it may behave differently on the scale of 93 billion light-years. We might be witnessing the first signs of a new physics, a deeper layer of reality that only becomes visible when you try to bridge the gap between the beginning of time and the present day. The tension of the Hubble constant is more than just a debate over a number. It is a crisis of consistency. It tells us that our narrative of the universe is missing a chapter. We are like detectives who have a clear picture of the crime scene and a clear picture of the suspect being arrested, but we cannot explain how they got from one place to the other. The James Webb Telescope is providing the high-resolution evidence we need to scrutinize every step of that journey. Every galaxy it catalogues and every redshift it measures is a data point that narrows the range of possibilities. We are searching for a bridge across the tension, a way to reconcile the smooth, predictable dawn of time with the frantic, accelerating expansion of the modern era. As you reflect on this scientific mystery, let the sense of the unknown settle over you. The universe is under no obligation to be simple or to fit perfectly into the boxes we build for it. The fact that we have found a discrepancy at all is a sign of how far we have come. We are now precise enough to know exactly where our ignorance lies. The Hubble tension is an invitation to curiosity, a signal that the most profound discoveries about the nature of space and time are still ahead of us. We are standing at the edge of a revolution in cosmology, looking through a golden mirror at a universe that refuses to be measured easily. The tension is the heartbeat of a living science, a reminder that the 93 billion light-year expanse still has the power to surprise us, to challenge us, and to force us to look deeper into the infrared shadows for the truth. Through the work of the whispering scientists and researchers across the globe, we are slowly peeling back the layers of this paradox. We are checking the distances, verifying the redshifts, and questioning the constants. We are participants in a great cosmic trial, where the evidence is light and the verdict is the secret of existence itself. The stretching of the spectrum was the first clue. The tension of the expansion is the second. As we move from the speed of the universe to the sheer number of worlds it contains, we realize that the scale of our ignorance is matched only by the scale of the cosmos itself. The 93 billion light-year sphere is a vast, beautiful, and tense reality, and we are just beginning to feel its pulse in the profound stillness of the 93 billion light-year expanse. A new and staggering reality is beginning to take shape. For decades, the consensus among astronomers was that the observable universe contained approximately 200 billion galaxies. This estimate was based on the landmark deep field surveys conducted by the Webb Space Telescope, which counted galaxies in small, dark patches of the sky and extrapolated those numbers across the entire celestial sphere. It was a number that felt solid, a foundational pillar of our cosmic bookkeeping. However, as the James Webb Space Telescope has turned its golden eye toward those same empty regions of space, it has revealed a universe that is far more crowded than we ever dared to imagine. The galaxy density in Webb's infrared observations significantly exceeds the counts provided by any previous instrument. If these new observations represent the true average of the cosmos, the total number of galaxies in the observable universe is not in the billions, but in the trillions. This shift in scale is not just a minor adjustment to a ledger, it is a fundamental expansion of the potential for life, chemistry, and existence itself, leading us to a breathtaking estimate of 4,000 quintillion planets. To grasp the weight of this number, we must first look at the architecture of a single galaxy. Our own Milky Way is a vast, rotating disk containing approximately 200 billion stars. In the last 20 years of planetary science, we have learned that stars are not lonely objects. On average, every star in the sky is orbited by at least one planet. This means there are roughly 200 billion planets in our galaxy alone. When we believed there were only 200 billion galaxies in the universe, the total planetary count was already incomprehensible, roughly 40 quintillion. But the Webb telescope has shattered that ceiling by revealing that the universe is 10 times more populated with galaxies than we thought. The number OF potential worlds has jumped tenfold. We are now looking at a cosmos that likely holds 4,000 quintillion planets, a 4 followed by 21 zeros. It is a scale of reality that renders our traditional concepts of rare or unique entirely obsolete. The increase in these galaxy counts comes directly from Webb's ability to perceive the invisible. Many galaxies that appeared as faint, indistinct smudges, or were entirely absent in Hubble's visible light images, show up with startling clarity in the infrared. Webb can see through the thick veils of cosmic dust that act as curtains, hiding entire populations of stars. Furthermore, because of the stretching of the spectrum, the most distant galaxies have shifted their light into wavelengths that only Webb can capture. We are finding that the empty spaces between the galaxies we already knew about are actually filled with thousands of smaller, fainter, or more distant systems. The universe is not a sparse collection of island universes, it is a dense, overflowing sea of matter. Early results from Webb's wide-area surveys are confirming that this higher density is not a statistical fluke or a local anomaly. It is the true face of the 93 billion light-year expanse, a reality where the sheer abundance of matter is the defining characteristic of existence. The philosophical and scientific implications of 4,000 quintillion planets are profound. If we assume that even a tiny microscopic fraction of these worlds resides in the habitable zone, the region around a star where temperatures allow for liquid water, the number of potentially life-bearing planets still reaches into the quadrillions. The cosmos is so vast, with so many billions of years of opportunity for chemistry to organize into biology, that the idea of Earth being the only site of life becomes statistically impossible. We are living in a universe that is a near-infinite laboratory of evolution. On some of these 4,000 quintillion worlds, mountains are larger than our atmosphere. On others, oceans of liquid methane churn under frozen skies. There are planets orbiting twin suns, planets drifting alone in the dark between galaxies, and planets so dense that gravity would crush a human in a heartbeat. Every variation of physics and chemistry that is allowed by the laws of nature is likely playing out somewhere in the darkness right now. This realization brings a strange kind of comfort. While it displaces humanity from any sense of being the center of the universe, it connects us to a much larger, more vibrant story. We are one outcome among trillions of instances where the universe has tried its hand at creating something complex. The light that Webb captures from the most distant of these galaxies is a reminder that the seeds for all these planets were sown in the very first moments of the cosmic dawn. The heavy elements needed to build rocky worlds, the iron, the silicon, the oxygen, were forged in the hearts of the first stars and scattered across the filaments of the cosmic web. We are looking at a manufacturing process that has been running for 13.8 billion years. The 4,000 quintillion planets are the finished products of that ancient industry. Despite this staggering abundance, we are faced with the haunting reality of isolation. Most of these trillions of galaxies and quintillions of planets lie at such vast distances that we can never hope to visit them or even communicate with any civilizations that might inhabit them. They are beyond the reach of our signals and the speed of our fastest probes. Many of them are already receding from us faster than the speed of light due to the accelerating expansion of space. We can see them, we can count them, and we can marvel at their existence, but we are separated from them by a gulf of space-time that is effectively permanent. We are part of a populous universe, yet we exist in a state of cosmic solitude, locked within our own observable sphere. As you settle into the quiet of the night, let the number 4,000 quintillion rest in your mind like a heavy, peaceful blanket. It is a number that represents the infinite variety of the cosmos, the endless possibilities of what might be happening. On a world circling a star in a galaxy we only just discovered, the 93 billion light-year expanse is not an empty void. It is a garden of worlds, a vast and crowded expanse of potential. For every grain of sand on every beach on Earth, there are 10,000 stars in the sky, and around almost every one of those stars, a planet is spinning in the silence. The James Webb Telescope has not just expanded our map, it has expanded our sense of belonging. We are residents of a universe that is far more fertile and magnificent than we ever imagined, a reality where the darkness is merely the backdrop for an unimaginable number of worlds. Through the work of the whispering scientist, we are learning to navigate this new crowded map. We are moving from a universe of hundreds of billions to a universe of trillions, and in doing so, we are finding our true place in the scale of things. We are a single point of awareness in a sea of 4,000 quintillion possibilities. The gold-coated mirrors of Webb have shown us that whenever we think we have reached the limit of what exists, we need only look a little deeper to find more. The census is not yet finished, and the count of worlds continues to grow. As we move from the abundance of planets to the ultimate boundary of our vision, we realize that the 93 billion light-year horizon is the final, most mysterious layer of the past we are allowed to see. In the profound stillness of the cosmic night, we finally come to the edge of everything we are permitted to know. This is the 93 billion light-year horizon, the ultimate boundary of the observable universe. To stand at this threshold is to confront the most significant paradox of our existence, the fact that we can see much further than light has had time to travel. As we have explored, the universe is 13.8 billion years old, yet the distance to the furthest objects we can detect is 46.5 billion light-years in any direction. This creates a total diameter of 93 billion light-years, a sphere of visibility that contains every galaxy, every black hole, and every atom of dark matter that has ever touched our reality. This horizon is not a physical wall or a cage made of matter, it is a limit imposed by the speed of light and the relentless expansion of space. It is the final layer of the past, a shimmering curtain of ancient radiation that marks the beginning of time itself. To understand why this horizon exists, we must imagine the universe as a vast ocean of light. When the Big Bang occurred, the cosmos was a hot, dense plasma that was opaque to radiation. For 380,000 years, light was trapped, bouncing between particles like a prisoner in a crowded room. Eventually, the universe cooled enough for atoms to form, and suddenly the fog cleared. Light was finally free to travel across the void. The very first light to escape this primordial fog is what we now see as the cosmic microwave background, and it forms the physical edge of our 93 billion light-year sphere. This light has been traveling for nearly 14 billion years, but because the space through which it moved was constantly stretching, the point from which that light originated is now over 46 billion light-years away. The horizon is the limit of our causal universe. Anything beyond this distance is moving away from us so fast that its light will never reach us, no matter how long we wait. The 93 billion light-year horizon is a deeply humbling concept because it reminds us that the observable universe is not the same thing as the total universe. We are living inside a bubble of light, and we have no way of knowing how large the ocean truly is outside that bubble. Some cosmological models suggest that the universe is infinite, stretching on forever with an endless supply of galaxies and stars that we will never see. Other models propose a finite but unbounded universe, like the surface of a sphere, where the total volume might be hundreds of times larger than our observable portion. Whatever the truth, the horizon remains our absolute limit. We are like sailors in the middle of a vast sea. We can see as far as the curve of the earth allows, but we know there is much more water beyond the line where the sky meets the waves. The James Webb Telescope allows us to see right up to the edge of this cosmic shore, capturing photons that have been struggling against the expansion of space since the very dawn of time. There is a haunting temporal quality to this horizon, because looking into distance is the same as looking into the past. The 93 billion light-year boundary represents the now of the Big Bang. When we look at the most distant galaxies, we are seeing them as they were billions of years ago. But if we could look even further, past the first stars and into the very edge of the horizon, we would see the universe as it was at its moment of birth. The horizon is a graveyard of time where the earliest events of the cosmos are preserved in a state of eternal redshift. As space expands, more and more objects are crossing this horizon, disappearing from our view forever. Because the expansion of the universe is accelerating, the treadmill of space is moving faster than the runner of light. Galaxies that we can see today with the Webb telescope will eventually be pushed beyond the 46 billion light-year mark. Their light will fade, Their images will freeze in time, and they will vanish into the unobservable darkness. This leads to a realization of cosmic isolation. Every second, the observable universe is losing information. We are living in a unique window of history where the evidence of the Big Bang is still visible. If we were to wait 100 billion years, the expansion would have carried every other galaxy beyond our horizon. Future residents of the Milky Way would look out and see a 93 billion light-year sphere of absolute empty blackness. They would have no way to know that trillions of galaxies once filled the sky. They would have no way to measure the expansion of space or the tension of the Hubble constant. To them, the universe would appear to be a single, lonely island of stars in an infinite void. Our ability to see the horizon today is a rare and precious privilege, a brief moment in the life of the cosmos where past is still within our reach. The James Webb Telescope is our most sophisticated tool for mapping this boundary. By observing the furthest galaxies, it is helping us determine the exact shape and curvature of the universe. If the universe were curved like a ball, we would see subtle distortions in the distribution of distant galaxies. But so far, Webb's data confirms space is remarkably flat. This flatness suggests that the universe is likely much, much larger than our 93 billion light-year bubble, perhaps even infinite. The horizon is merely a consequence of our perspective, a circular shadow cast by the finite speed of light. It tells us that we are part of a reality that is far more vast than our senses can perceive, a cosmos that continues to grow and extend far beyond the limits of our most powerful mirrors. As you reflect on the 93 billion light-year horizon, let the scale of it bring a sense of peace. We are small, yes, but we are the eyes of the universe, looking back at our own beginning. The horizon is not a wall that shuts us in, but a horizon that invites us to wonder. It marks the edge of the known, but it also hints at the infinite unknown that lies beyond. The light that Webb captures is a bridge between our tiny world and the very limits of existence. We are standing on a speck of dust, measuring a sphere of 93 billion light-years, and in doing so, we are participating in the grandest story ever told. The horizon is the final layer of the past, the quiet, glowing boundary of our reality, and it reminds us that no matter how much we learn, the universe will always hold a secret that remains just out of reach. Through the mirrors of the whispering scientist, we have charted the course from the first stars to the ultimate edge. We have seen the too much light of the early galaxies and the monsters in the darkness. Now, as we sit at the horizon, we realize that the story of the universe is a story of expansion and light. The 93 billion light-year expanse is our home, our laboratory, and our mystery. As we move from this boundary to the final forces that will determine the end of time, we carry with us the knowledge that we have seen as far as the light will allow. We have reached the visible edge. What lies beyond is the realm of pure theory and eternal expansion. In the profound stillness of the 93 billion light-year expanse, a force we cannot perceive, a force known only as dark energy, is dictating the ultimate destiny of everything we send, everything we are. While gravity is the architect of the cosmic web and the builder of galaxies, dark energy is the relentless expander, the silent power that pushes space apart. It comprises approximately 68% of all that exists, dwarfing the matter in stars, the dust in nebulae, and even the invisible scaffolding of dark matter. To understand the fate written in dark energy is to realize that the universe is not a static structure, but a dynamic and accelerating entity that is moving toward a conclusion dictated by the properties of the vacuum itself. The James Webb Space Telescope, by peering into the deep infrared past, is providing the critical data needed to determine whether the universe will end in a slow, cold fade or a violent, catastrophic tearing of the fabric of reality. Dark energy is perhaps the most unsettling discovery in the history of science because it behaves in a way that defies our intuition about the physical world. In every other instance we know of, things become less dense as they expand. If you have a cloud of gas and you double its volume, the particles become more spread out. But dark energy does not dilute. Its density remains constant even as the space it occupies grows. This means that as the universe expands, it creates more space, which in turn contains more dark energy, which then pushes the expansion even faster. It is a self-reinforcing growth engine that has been dominating the evolution of the cosmos for the last 5 billion years. Before that era, gravity was the primary influence, slowing the expansion as matter pulled on itself. But dark energy eventually reached a tipping point, where its repulsive force overcame the attractive pull of matter. We are now living in a universe that is accelerating away from itself, and that acceleration is the key to our ultimate fate. The fate of the 93 billion light-year sphere depends entirely on how dark energy behaves as the eons pass. If the strength of dark energy remains perfectly constant, a value known to physicists as the cosmological constant, then the universe is destined for a big freeze. In this scenario, expansion will keep accelerating forever. Slowly, the great cosmic web will begin to unravel as the voids expand and the filaments are stretched thin. While gravity will hold our local group of galaxies together, every other cluster in the universe will recede beyond our cosmic horizon. Trillions of years from now, the Milky Way's night sky will be a dark and lonely place, containing no light from any other galaxy. Eventually, even the stars will burn out, leaving behind cold cinders in an ever-expanding, freezing void. It is a long, quiet sunset of existence, where the universe ends not with a bang but with a slow, inevitable cooling into absolute zero. However, there is a more extreme possibility written in the equations of dark energy, one that depends on whether this force increases in strength over time. This is the theory of the Big Rip. If dark energy is not constant, but instead becomes more powerful as the universe ages, its repulsive force will eventually overcome every other force in nature. First, it will overcome the gravity holding superclusters together. Then, it will tear apart individual galaxies, sending stars flying into the darkness. As the acceleration continues to mount, it will overcome the gravity of solar systems, pulling planets away from their suns. In the final, terrifying moments, dark energy would become strong enough to overcome the electromagnetic and nuclear forces that hold matter together. The Earth itself would be pulled apart, then molecules, then atoms, and finally the very fabric of space-time would be shredded into nothingness. The Big Rip is a violent end to the story of the cosmos, a total dissolution of structure where the vacuum itself becomes a weapon of mass destruction. The James Webb Telescope is our most vital tool for distinguishing these fates. By measuring the expansion rate across billions of years of history, it allows us to calculate the equation of state for dark energy. If Webb finds that the acceleration was different in the early universe compared to what we see today, it would suggest that dark energy is dynamic. This data would tip the scales toward a more complex and potentially more violent end. Every high-redshift galaxy that Webb catalogues is a marker that helps us trace the history of this acceleration. We are looking for the jerk, the rate at which the acceleration itself changes. If we can find that value, we can read the final chapter of the universe before it is even written. We are currently living in the era of dark energy dominance, a brief window where we can still see the evidence of how this force took control of the 93 billion light-year expanse. There is also the theoretical possibility of a big crunch, though it seems unlikely given our current observations. In this scenario, dark energy would eventually fade or reverse its sign, allowing gravity to take control once more. The expansion would slow to a halt, and the universe would begin to contract. Galaxies would rush toward each other, the cosmic web would collapse, and the universe would end in a high-temperature inferno as everything is crushed back into a singularity. However, since the discovery of the accelerating expansion in 1998, the Big Crunch has moved from a leading theory to a distant outlier. The data from Webb and other observatories consistently shows a universe that is being pushed apart with increasing vigor. The fate written in dark energy appears to be one of perpetual growth and eventual isolation. As you reflect on the ultimate fate of the cosmos, let the scale of these forces bring a sense of perspective. We are observers of a drama that spans billions of years and trillions of miles. Dark energy is the invisible hand that is slowly turning the lights out on the rest of the universe, separating us from the 4,000 quintillion planets we have only just begun to count. It is a reminder that the 93 billion light-year horizon is a temporary gift, a bubble of visibility in a reality that is destined to stretch beyond our reach. We are fortunate to exist in this specific epoch of cosmic time, when the balance between gravity and dark energy allows us to see the full architecture of the Webb and the history of the light. Through the golden eye of the James Webb Telescope, we are learning to measure vacuum weight and stretching strength. We are the first generation of humans to know with mathematical certainty that the universe has an expiration date. Whether it is a slow freeze or a sudden rip, fate is written in the very empty space that surrounds us. But this knowledge does not diminish our existence, it enhances it. It makes our study of the stars and our search for life even more urgent and meaningful. We are a part of the universe that has developed the ability to calculate its own end, turning the mystery of dark energy into a roadmap for the future of time. As we move to our final reflection on James Webb's revelations, we carry with us the weight of 93 billion light-years and the silent, accelerating power of the dark energy that will eventually carry it all away. In the profound and echoing silence of the 93 billion light-year expanse, we have reached the final layer of the past. Our journey through the revelations of the James Webb Space Telescope has taken us from the golden mirrors, orbiting 1,000,000 miles away, to the very edge of the observable horizon, where time and space dissolve into the primordial fire of the beginning. We have witnessed the impossible galaxies that broke our models of creation, the monsters that grew too fast in the infant darkness, and the invisible highways of dark matter that guide the flow of all existence. Every photon we have discussed and every red-shifted signal we have decoded is a thread in the grand tapestry of a universe that is far older, larger, and more complex than we ever dared to imagine. As we stand at this final threshold, we are not just looking at distant lights, we are looking at the deepest roots of our own identity. We are the witnesses to a 13.8 billion-year-old story that is still being written in the stretching fabric of the vacuum. The James Webb Telescope has shown us that the universe we perceive is only the most recent chapter of a much longer narrative. By peering through the dust and capturing the infrared whispers of the first stars, it has peeled back the final layer of the cosmic past. We now know that the Dark Ages were not a silent void, but a frantic nursery where the first structures assembled with a speed that defies our current laws of physics. We have seen that the universe did not wait to become magnificent. It exploded into brilliance, creating massive galaxies and supermassive black holes when it was barely a fraction of its current age. This realization has forced a fundamental shift in our perspective. We no longer see the cosmos as a slow, predictable clockwork mechanism, but as a dynamic, efficient, and often surprising engine of creation. The 93 billion light-year horizon is the ultimate boundary of this engine's work, a shimmering curtain that separates the era of light from the era of pure energy that came before. As we reflect on the scale of these discoveries, we must confront the reality of our own smallness, but also the magnitude of our achievement. We occupy a single, fragile world, orbiting an average star in a galaxy that is just one among trillions. Yet, from this tiny vantage point, we have built a tool capable of catching light that has been traveling since the dawn of time. We have found a way to measure the tension of the expansion and the weight of the dark energy that will eventually determine our fate. We have estimated the existence of 4,000 quintillion planets, each a potential stage for the same drama of evolution that produced us. This is the ultimate gift of the James Webb Telescope. It has given us a sense of context that is as vast as the heavens themselves. We are not separate from the cosmic web. We are its children, composed of the same heavy elements forged in the hearts of those first, impossible stars. There is a deep, quiet peace in the realization that the universe is so much more populated and structured than we once thought. The census of 800,000 galaxies in a single patch of sky is a reminder that the darkness is never truly empty. It is filled with the potential for life, the beauty of gravitational architecture, and the persistent movement of light. Even as dark energy pushes the galaxies further apart and the voids grow larger, the information carried by those ancient photons remains a bridge across the silence, We are the first generation of our species to see the true scale of the universe, to look at the 93 billion light-year horizon and understand exactly what we are seeing. We have moved beyond the myths of the past into a reality that is far more wondrous than any story we could have invented. The final layer of the past is not an end, but a beginning, a foundation upon which we will build our future understanding of space and time. As you drift into the quiet reflections of this cosmic journey, let the weight of 93 billion light-years settle over you like a heavy, protective blanket. The universe is a place of incredible scale, but it is also a place of order and connection. The filaments of the web, the highways of dark matter, and the light of the first galaxies all tell a story of a reality that is unified by the laws of physics and the passage of eons. We are part of a grand expanding balloon of reality, moving together through a history that is written in the stars. The golden eye of Webb will continue to stare into the darkness, finding new galaxies, uncovering more monsters, and pushing our horizon even further into the unknown. We are the explorers of the deep past, the cartographers of the infrared, and the dreamers who look at the night sky and see not just points of light, but the history of everything. The 93 billion light-year expanse is a mirror of our own curiosity. Every discovery we make about the early universe is a discovery about the processes that allowed us to exist. We are the result of the too much light and the monster stars that cleared the fog of the infant darkness. We are the beneficiaries of the dark matter highways that funneled gas into the milk. Way. Our history is etched into the red-shifted spectrum of every distant galaxy. As we close this chapter of our exploration, we do so with a profound sense of gratitude for the light that has traveled so far just to reach us. The universe is vast, it is tense, and it is accelerating, but it is also beautiful and filled with a logic that we are finally beginning to grasp. As the lights of the distant clusters fade into the background of your thoughts, remember that the 93 billion light-year horizon is always there, waiting to be explored. We have seen the true scale of the universe, and it is a scale that invites us to be both humble and bold. We are the whispering scientists, the ones who listen to the echoes of the Big Bang and find the stories hidden in the infrared shadows. The journey through the cosmos is a journey without an end, for every answer we find only leads to a deeper and more magnificent question. Sleep now in the knowledge that you are a part of this vast interconnected web, a single point of light in a universe that is 93 billion light-years across and full of wonder. The final layer of the past has been revealed, and the future of our discovery is as infinite as the stars. The golden mirrors are still watching, the light is still traveling, and the universe is still stretching. We have witnessed the James Webb just revealed the true scale of the universe, and our perspective will never be the same again. In the silence between the galaxies and the heat of the first stars, we find our home. Good night to the 4,000 quintillion planets. Good night to the cosmic vine, and good night to the 93 billion light-year horizon. We are children of light, and our story is eternal.